This is ENVE 445, Water and Wastewater Treatment Engineering. Module 3, Wastewater Treatment Engineering. In this module, we're going to get an overview of wastewater treatment. We're going to learn about wastewater flows, collection, and characteristics, preliminary and primary treatment, secondary biological treatment, tertiary treatment and disinfection, sludge management, and small flow systems. The first part is an overview of treatment, flows, and characteristics of wastewater. Our learning objectives for this first part are to calculate flow rates based on land use types, infiltration, inflow, and peak hourly flow rates, to identify which flow rates are to be used for design purposes, to describe basic physical chemical properties of wastewater, to calculate concentrations and loadings of constituents, and to describe typical wastewater treatment processes. Overall, we can consider wastewater treatment to be one step in the overall sanitation service chain. So sanitation service chain starts with the user interface, which is like the toilet, the drainage structures that are typically found at households, businesses, public places, industry, as well as any on-site collection, containment, storage, and treatment. In a decentralized sanitation system, you might have treatment and storage on site, whereas in a centralized or semi-centralized sanitation system, the containment and collection is done using a series of pipes, typically, which direct the wastewater to a centralized treatment plant. In the on-site system, there is still often centralized treatment, and therefore the conveyance of fecal sludge or septage from the on-site sanitation system might happen using a vehicle as opposed to a pipe system. So we have the user interface, on-site sanitation, if applicable, followed by conveyance, and then centralized or semi-centralized treatment. After treatment, there's also conveyance to the final point of end use, return to the environment, or reuse of water or biosolids. So the wastewater treatment is really just this centralized or semi-centralized treatment component of the overall service chain. When we talk about sanitary sewer collection, this is that second step or third step of the chain, which is conveyance. And in a conventional sewer system, we have two different types of systems to collect and convey sewage to a centralized plant. The first is a combined sewer system. This is something you might see in older cities where the stormwater and the wastewater are combined together and collected and conveyed using a single network of pipes. More common nowadays is to see separate sewer systems where you've got one sewer system dedicated for the stormwater flows and the other sewer system dedicated for the sanitary sewer flows. So these are two different types of sewer collection systems that you might see in the United States. As you can see, the network of sewer collection systems looks more like a tree rather than a loop like you would see for the distribution system of potable water. In sanitary sewer, the sewage is conveyed usually via gravity for the most part. So you don't have pipes connected in loops. You have a sewer main, which is connected to several branches that branch out onto the streets. And those branch lines have individual service connections for the houses or the businesses or any other use. Here's an example of what those service connections typically look like. So if you have a main line or a branch line in the city street, you've got the property line. You'll have a sewer clean out, which can be accessed in the event of blockage. And then you've got the private sewer lateral line, which is maintained by the property owner. And that comes from the household where you would have connections like from the kitchen, from the laundry room, from the bathroom. Some factors that affect the flow and strength of wastewater are water availability. So in some locations where water is more scarce, the consumption of water tends to be less, and therefore the flow of wastewater per capita tends to be less. Uh, so that goes along with climate. So warmer climates might induce a greater water consumption, but climates that are more dry might induce a lower consumption of water and lower flow rates of sewage per capita. The community size also is a factor that influences flow. So larger cities generally present larger per capita water consumption because you have a lot of commercial and institutional activities. In smaller cities, you might see lower per capita water consumption. The economic level of the community, of course, as well, because a higher economic level would tend to have more commercial and industrial or institutional uses, which would contribute to higher flow rates of sewage. Metering of household consumption in the US, metering is pretty much universal, but in some places the water is not metered. So if the water is metered, meaning that the user is paying per unit volume that's used, then you would tend to have lower sewage flow rates than compared to a location where the water is paid for just as a flat rate. The water cost, the water pressure, these all influence how much water is used in a household. And then system losses as well. So some systems that are very old and have quite a few leaks might have lower flow rates because there's not all of the sewage is getting to the treatment plant. So wastewater flow rates, just like water demand, follow a diurnal variation. So you've got very low flow rates experienced in the nighttime, in the early hours of the morning. And then after the people tend to wake up, early morning hours, you tend to get a peak, an initial peak of sewage flow. These peaks are a little bit delayed from the peaks of water consumption because to allow for some time for the water to travel through the pipe systems. So this peak in the morning tends to be the highest peak in most cases. Then there might be a decrease in the flow rate received towards the early afternoon, followed by another peak in the evening as people are using water again in the late hours of the evening. And then after people tend to go to sleep, then you would see the flow rate come down again. So this diurnal variation can be very peaky in the case of small systems, especially systems without flow equalization, or the peaks might be more gradual, and this is more common in larger cities where there's more mixing and you have different travel times of the sewage to get from the place of where the user's located, like the household, all the way to the centralized treatment system. So in general, we have some kind of rules of thumb of what the peaking factor might be. So Q max being approximately equal to 2 times the average flow rate, Q minimum being approximately equal to 0.5 times the average flow rate. However, like I mentioned, this can vary from system to system. It depends on the size of the system. The best approach to determine peaking factor is to pay attention to local regulations and guidelines for design, or to get some flow data from a similar nearby plant that would have similar peaking characteristics. And you can see here's some data from 2 studies that show for larger populations, you have smaller peaking factors. For smaller populations, you have larger peaking factors. Wastewater flow rates also include what we call inflow and infiltration, or I&I. So infiltration is what happens during both dry periods and wet periods. And it includes steady inflow in this graph that you see to the right. Inflow, on the other hand, mostly happens during rainy conditions. If we, in addition to what we would consider the steady inflow, which we typically lump together with infiltration. So inflow comes from things like foundation drains, cooling water discharge, direct connections to the sewer system, roof leaders that are connected to the sewer system, but for example, they probably shouldn't be connected, but there's some kind of historical interconnection between yard or area drains, roof leaders into the sanitary sewer. Access port covers, so rainwater seeping in through those port covers, and storm sewer cross connections, like I said, that shouldn't be there, but might exist due to mistakes in the construction in the past. Infiltration typically happens because there might be high water tables, high groundwater levels that could allow groundwater to seep in through cracks and seams in the pipe, as you can see in this photo up here. So you can have the infiltration, which might occur year round because the groundwater table is usually somewhat steady. Or you might just have infiltration during the wet period if the groundwater table rises, and then reduced infiltration during the dry period. On top of that steady inflow and steady infiltration, you have the peaking demands, the peaking flow rates that are coming from the users, right? Like we saw with that typical diurnal peak. And in addition to that peak, you would have on top of that inflow, which happens during rainy conditions. So during a rain event, the inflow would tend to usually have a very high peak, followed by a longer release period where it rapidly comes down, but then you have a period of several days, which we call delayed inflow, before it gets back down to the normal levels under dry conditions. All right, so there's different ways that we can classify wastewater flow rates, and flow rates not only vary diurnally, but they also vary seasonally. So we might have lower flow rates in the dry period and then higher flow rates in the wet period due to things like inflow and infiltration. So the average daily dry weather flow is defined as the base flow plus the dry weather infiltration. The peak daily dry weather flow would be calculated as the base flow multiplied by a peak factor plus the dry weather infiltration. So it's important to note that the peaking factor is applied only to the base flow, but not to the infiltration flow. Because again, that peaking factor is really meant to account for the variations that happen at the household or at the residential or industrial or public facility. The average daily wet weather flow is equal to the base flow plus the dry weather infiltration plus the additional wet weather inflow and infiltration. And then the peak wet weather flow would be the same thing. However, we would apply that peaking factor to the base flow. And it's important to know your flow rates when we talk about sewage. So typical flow rates from a community in the United States tend to be approximately 100 gallons per person per day, which is about 380 liters per person per day. However, it can vary greatly from one city to the next. So it can be anywhere from 50 or even less than 50 in some communities, gallons per person per day, to as high as 250 gallons per person per day. Flow rates that are to be used for design purposes are usually specified in design guidelines. So again, it's important to pay attention to local design guidelines and adhere to those standards when designing a system. However, in general, as a general rule, this is how we might classify flow rates. So you have the average dry weather flow, the average wet weather flow. This is the average of daily flow data for dry and or wet weather periods. We've got the instantaneous peak flow rate, which would be the highest recorded flow rate for a reporting period. And in the US, reporting periods are generally monthly. It's important to note that the instantaneous peak flow rate may actually underestimate the true peak. So in some cases, if we're measuring flow rate in a system on an interval, so it's not continuous measurement of flow rate, this peak during a rainfall period happens very quickly. It goes up very quickly and it comes back down very quickly. So if we're not measuring flow rates continuously, we might actually miss that true peak. We might measure our flow rate here, and then we measure our flow rate again a couple hours later, and then maybe we measure it again a few hours later, and we see this kind of square peak, but we may have actually missed the true peak, which could have been in between the two times that we happen to measure. So many facilities now have online real-time measuring and monitoring of flow rates, but some systems, especially in smaller towns, may do the flow rate measurement manually. All right, so that's the instantaneous peak flow rate. It tends to happen during rain periods. We've also got peak hourly flow rates, which are the maximum sustained hourly flow rate that occurs during a 24-hour period. These Flow rates tend to be used to size pipes and maybe also some reactors with short retention times. The peak daily or weekly flow rate is the maximum flow rate that occurs over a 24-hour period or over a 7-day period. And this is often used to size reactors with long hydraulic retention times or systems with flow equalization. The maximum monthly flow rate would be the maximum daily flow rate sustained for a period of 1 month. It's often reported as the 30-day period that occurs within the reporting period for the discharge permit. So these are some terminologies and which ones of these flow rates are typically used for design purposes. When we classify wastewater, we can break it down into several different parts. And with increasing trends towards water reuse, we may see some communities start to break apart these different wastewater streams and have different ways of handling them. So in general, we can classify wastewater or sewage as gray water or black water. So gray water would be anything that comes from what you can see: dishwasher, kitchen tap, washing machine, shower, bathroom tap, anything except for the toilet. And we would have gray water, which is considered heavier, meaning it has more contaminants coming from the washing machine, the kitchen tap, the dishwasher. And then we would have gray water, which tends to be lighter, not as contaminated, a little bit less turbid. That would come typically from the bathroom tap, from the shower. Black water can then be broken up into brown water and urine. So in systems where the toilets are urine diverting toilets, the urine can be separated out and managed in a different way, since urine contains most of the nutrients, but very, very few pathogens and often no pathogens. Brown water would consist of feces plus water, water as being in systems where water is typically used for flushing. All right, so together those two things make black water. So we have black water plus gray water, which would equal sanitary sewage. So getting back to typical indoor water use in the United States, here's a breakdown of flow rates per capita. This is shown as gallons per person per day or liters per person per day for different use types. So in the bath, for clothes washing, for dishwashing, from faucets, from the shower, etc. And you can see with current levels of conservation, the flow rate of each of these different use categories. And with extensive conservation, like you might see in some water scarce environments, you can see by how much some of these decrease. So uses such as bath, wastewater from the bath, that would tend not to change very much with conservation. However, clothes washing, laundry wastewater would tend to decrease quite a bit, given the technologies that are now being commonly implemented in washing machines. And the same goes true for toilet flushing. You've got low flow toilets as well. And some of these change more drastically than others when you talk about water conservation. All right, so taking a look at this table and just considering the breakdown of different types of wastewater, I want you to think about how much water would be saved per day in a household of 5 people if the faucet water from the bathroom was reused for flushing. So imagine a toilet that was retrofit so that the water that goes down the drain after washing hands in the faucet in the bathroom, that water gets directly added to the tank or added after some treatment, added to the toilet tank for use as flush water. How much water would be saved per day? All right, now I want to talk a little bit about the relationship between flow rates, concentrations, and loadings. And this is an extremely important concept that we're going to continuously use throughout the rest of this course in the design calculations and example problems. So flow rate, we already know, is the volume of wastewater that comes into a system, right? Concentration would be the mass concentration of some constituent. Let's take as an example nitrate. So we'd have a concentration of nitrate, milligrams per liter, usually. And then the flow rate might be liters per day, or cubic meters per day, or gallons per day. A load is defined as the product of flow times concentration. All right, so if we have a flow rate of 100 liters per day, meaning 100 liters are passing by some point in a pipe every single day, we've got a concentration of 3 milligrams per liter of, let's say, nitrate. That means that if we were to take a 1 liter sample container and collect 1 liter of water, there would be, on average, 3 milligrams of nitrate in that sample. The loading would be 3 milligrams per liter times 100 liters per day, which comes out to 300 milligrams per day. What that means is that 300 milligrams of nitrate would tend to pass by this point in the pipeline every single day. All right, so to keep in mind, the key concept here is that flow rate is unit volume per day, concentration is unit mass per unit volume, and loading is unit mass per day, or unit mass per unit time. Let's do 2 example problems. The first example is wastewater from a residential community is 120 gallons per person per day, containing 200 milligrams per liter of BOD and 240 milligrams per liter of TSS. So I want you to compute the daily mass loading of BOD and TSS per person. All right, let's do another example. In this example, industrial wastewater has a flow rate of 2.3 million gallons per day, a BOD of 21,600 pounds per day, and TSS loading of 13,400 pounds per day. So calculate the BOD and TSS concentrations in the wastewater. So in both of these example problems, we are making conversions between concentrations and loadings. So remember that loading is equal to concentration times flow rate. So if we have a concentration and a flow rate and we want a loading, we use it like this. Of course, in some cases we might have a loading and we're being asked for a concentration, so we would just rearrange that equation. Very simple. All right, so the first one to start out is we've got a flow rate of 120 gallons per person per day. And we've got a concentration of 200 milligrams per liter BOD, 240 milligrams per liter TSS. Perhaps the trickiest thing with this type of problem is the conversion between English and SI units. So you can just remember that 1 milligram per liter is equivalent to 8.34 pounds per million gallon. Okay, so if we convert these two concentrations to pounds per million gallon, we would multiply them by 8.34 and we get 1668 and 2002. All right, and this is BOD, this one is TSS. So now if we take this flow rate, it's in gallons per person per day instead of million gallons. So we can multiply this by, divide this by 1 million to get million gallons per person per day. So that would be 0.00012 million gallons per day per person. And same thing for the TSS. Now we're just multiplying 1668 times 0.00012 and multiplying 2002 times 0.00012 to get our final answer, which comes out to be approximately 0.20. The units there are pounds per person per day. And 0.24 pounds per person per day. So this example just kind of shows also that when you're talking on a per capita basis for residential wastewater, where a common value used in some areas is 120 gallons per person per day, whatever your concentration is, that's approximately equal to the loading if you just in pounds per person per day if you divide it by a factor of 100 or 1000. All right, so 0.2 pounds per person per day, 0.24 pounds per person per day. Second example. All right, in the next example, we've got industrial wastewater with a flow rate of 2.93 million gallons per day. And we've got loadings of BOD and TSS. So the BOD loading is 21,600 pounds per day, and the TSS loading is 13,400 pounds per day. All right, so in order to get a concentration, we would just manipulate this equation, taking the loading and dividing it by the flow rate. That's going to give us the units pounds per million gallon. So if we take 21,600 divided by 2.93, that gives us 7372. And 13,400 divided by 2.93 gives us 4,573. And again, this is pounds per million gallon. Now, if we want to express those concentrations as milligrams per liter, which is more typical, again, we just use that factor. 1 milligram per liter is equal to 8.34 pounds per million gallon. So we divide these numbers by 8.34, and that gives us 884 and 548. And the units there is milligrams per liter. Okay, now that we can understand a little bit about flow rates, loadings, concentrations, let's talk about how to actually determine those flow rates. So let's start with estimating infiltration and inflow. So inflow, again, is defined as the water discharged into sewer pipes or service connections from things like foundation drains, roof drains, yard drains, discharges from commercial and industrial establishments. In some municipalities, in some communities, 5 gallons per person per day is used for planning purposes. In other regulations, you might see that inflow is lumped in with the per capita flows. So for that base flow, again, being typically like 80, 100 gallons per capita per day, in some municipalities, they might just lump this assumption of inflow, lump that in with the per capita flow rates. And infiltration, on the other hand, is defined as the groundwater which enters sewers and building connections through defective joints in broken or cracked pipes and manholes. So this can be estimated using either the acreage method or the pipe diameter and length method. And we'll see some examples about how this is done. Both of these, inflow and infiltration, they can both be estimated also using wastewater flow records during wet and dry seasons. And that's actually the best way usually to get a good idea about what you might experience as infiltration and inflow is by looking at a similar system. Okay, so infiltration can be estimated again based on the acreage. So if you have a service area that is, let's say 2,000 acres, and it has a peak hourly domestic flow rate of 1.5 million gallons per day, we would take the rate, let's say 1,500 gallons per day per acre, multiply that by the acreage, and that would give us a good idea, rough estimate of what the infiltration might be, 3 million gallons per day in this case. All right, so this rate, gallons per day per acre, might be specified in the design guidelines. So maybe instead of 1,500 in some areas, maybe they'd use something more like 700 or 800. All right, so very simple method just based on the service area acreage. The second method is based on the pipe diameter and the pipe length. So this again uses a constant, which is expressed with the units gallons per day per inch diameter per mile of pipe, or liters per day per centimeter diameter per kilometer of pipe. And typical ranges are 200 to 500 gallons per day per inch per mile. This range between 200 and 500, it varies with respect to groundwater level, the pipe material, the age of the pipe, the materials, and the craftsmanship of the construction of structures, siphons, and other elements of the sewer system. So an example here, the way this calculation is done is, let's say we have 10 miles of 12-inch pipe, and let's say we're using a rate of 500 gallons per day per inch per mile. We would take 500 multiplied by 12 inches, multiplied by 10 miles. That would give us a value of 60,000 gallons per day for this stretch of pipe. So then you would take other stretches of pipe. Let's say you've got 5 miles of 15-inch pipe, and perform the same calculation to get the gallons per day from that stretch of pipe. At the end, once you've accounted for all different pipe materials and lengths, you would sum everything up to get the total infiltration flow rate. Let's do an example problem. Calculate the infiltration and compare this quantity to the average daily and peak hourly domestic wastewater flow rate for the following situation. We've got a sewered population of 24,000 people with an average domestic flow of 100 gallons per person per day, a peak hourly domestic flow of 240 gallons per person per day. We'll use an infiltration rate of 500 gallons per day per mile per inch. And we can consider a sanitary sewer system that has 36 miles of 4-inch building sewers, 24 miles of 8-inch street laterals, 6 miles of 10-inch submains, and 6 miles of 12-inch trunk sewers. So here we've got 4 different pipe sizes, and we've got the length of each of those pipe sizes. So you can set this up in like a table. Where we have the length of the pipe in miles, and we have the diameter of the pipe in inches. So 36 miles of 4-inch pipe. We've got 24 miles of 8-inch pipe, 6 miles of 10-inch pipe, and 6 miles of 12-inch pipe. Now remember, the rate that we're using is 500 gallons per day per mile per inch. So we need to get the products of these, which would be mile inches of pipe. So 36 times 4, 144. Next one, 192, 60, and 72. And then we sum together all those products, we get 468. The units here are inch miles. So it's 468 inch miles of pipe. Last step, take our rate, 500 gallons per day per inch per mile, times 468 inch miles. And that gives us 234,000 gallons per day. So that's what we would use for our estimate of infiltration here. Let's do another example. Consider a large city which has measured the high flow rates during the wet season. During the dry period of the year, when rainfall is rare and infiltration is negligible, the average daily flow rate is 120,000 cubic meters per day. However, during the wet weather period, the groundwater tables are elevated, and the flow rate is an average of 230,000 cubic meters per day. This is not considering days during significant rain events or right after significant rain events. Now, during a recent storm, the hourly flow rates were recorded during the peak flow period and for several days after the storm. And those Flow rates are shown in the figure here to the right. Compute the infiltration and inflow and determine if infiltration is excessive, where, let's say, excessive infiltration inflow is defined as anything that's greater than 0.75 cubic meters per day per millimeter of pipe diameter per kilometer of pipe length. So assume that the system has 10 miles of 18-inch pipe, 275 miles of 12-inch pipe, and 400 miles of 8-inch pipe. All right, so in this example problem, we've got different flow rates occurring during different seasons. So in the dry season, when we don't have any rainfall, so there's really no inflow, and we perhaps have a low groundwater table, so there's negligible infiltration. We've got a base flow rate of 120,000 cubic meters per day on average. And in the wet season, when the groundwater table increases and we've got infiltration because of that high groundwater table, when it's not raining, so we don't have that huge spike from inflow, our flow rate during the wet season is 230,000 cubic meters per day. So the first part here is just to determine the difference between infiltration and no infiltration. And we just do that by looking at the difference between those two flow rates. So 230,000 minus 120,000 equals 110,000 cubic meters per day. So we can assume that that comes from infiltration. The next part is to look at inflow. So for inflow, we know that that peak flow rate that happens right after the rain event, right as the rain event is in its prime, right? We've got a flow rate of 606,000 cubic meters per day. And by comparing that flow rate to the flow rate that we had 24 hours earlier, which would occur during the same peak or valley in the domestic flow rate, as you can see, we've got 340,000 cubic meters per day. So if we subtract those two from each other, this is going to give us that difference that's accounted for by the inflow that's experienced due to the rainfall. All right, so 606,000 minus 340,000 is equal to 266,000. And this would be our inflow. The next part of this is to calculate an infiltration and inflow rate by normalizing this by the amount of pipe we have and the size of each pipe. So we're told that the system has 10 miles of 18-inch pipe, 270 miles of 12-inch pipe, 400 miles of 8-inch pipe. In order to compare our rate with the local regulatory agency rate, which is expressed per millimeter of pipe per kilometer, we'll need to just convert these into the appropriate units. So 10 miles is approximately 16 kilometers, and 18-inch pipe is approximately 450 millimeter. We multiply those two together, 16 times 450 equals 7,200. The units there are millimeters, kilometers. We do the same thing for the 12-inch pipe and the 8-inch pipe, and then we add these three values. So 7,200 plus 132,900 plus 128,800, that gives us a total pipe length diameter of 268,900 millimeters, kilometers. So now we take our inflow and our infiltration, so that's 110,000 plus 266,000, and that equals 376,000 cubic meters per day. This is our I&I. All right, the last step is to take that infiltration inflow rate, 376,000 cubic meters per day and divide it by our pipe length and diameter, 268,900 millimeter kilometers. And that gives us our rate, which comes out to approximately 1.4 cubic meters per day per millimeter kilometer. So if we compare that to the regulatory agency, which says excessive ionized defined as anything greater than 0.75. So since 1.4 is greater than 0.75, we can say that the inflow and infiltration in this system is excessive. And that might warrant the need for replacing some of the aging, damaged sewer pipe infrastructure, or at the very least examining the condition of the existing sewer pipes. Now let's talk about wastewater constituents. So wastewater is mostly water, more than 99% water. However, the constituents in wastewater are particularly potentially harmful, right? They could contain pathogens, they contain a large amount of organic material and nutrients which need to be removed before the wastewater can be effectively discharged to the environment and or reused safely. And if we're talking about situations of reuse, like for non-potable reuse, in some cases we may not need to remove the nutrients because maybe the nutrients can be beneficial for irrigation purposes, for example. However, if the intended reuse is indirectly connected with potable water use, then we would need to achieve very high levels of pathogen reduction, very high levels of organic matter and solids reduction. So this table right here just shows for raw wastewater the approximate composition in terms of total solids concentration, total volatile solids, suspended solids, volatile suspended solids, BOD, and then nutrient concentrations in raw wastewater. This is based on a flow rate of approximately 120 gallons per person per day. And then the concentrations that you might expect to see after primary settling, and finally after secondary biological treatment. So you can see that some of these constituents are significantly reduced during primary and secondary treatment, whereas others, such as nutrients, especially phosphorus, and total nitrogen, may really only be reduced by a small amount or might stay consistent. All right, so taking a look at this table here and using your knowledge of wastewater concentrations and flow rates, loadings, what would be the percent removal of suspended solids by primary settling? And what would be the carbon to nitrogen to phosphorus ratio on a mass basis for average sanitary wastewater, raw wastewater? Let's talk about wastewater solids. So we can measure wastewater solids in terms of the total solids content, but we can also break that down into different parts. So the total solids can be broken down into the percent solids that are volatile, meaning that they would combust at a temperature of about 500 degrees or higher. Fixed solids, which would be inorganic, they would tend not to combust at high temperatures. Suspended solids, we can also break down the total solids composition into suspended solids and dissolved solids. So suspended solids being those that are suspended and can be removed by a filter. Dissolved solids would be that fraction of solids that are dissolved into the water itself. They're very small and would not be removed using a conventional filtration process. Since we can break up in these two different ways, volatile and fixed, and suspended and dissolved, we can also describe the fraction of volatile suspended solids versus the fraction of fixed suspended solids, as well as the volatile dissolved solids and the fixed dissolved solids. So you have many different ways that solids concentrations can be represented. And we often use volatile suspended solids a lot in wastewater treatment calculations because that's a surrogate measurement in secondary treatment, biological treatment. It's a surrogate measurement for the amount of biomass that's in the system. So it helps us keep track of how much active biomass we have in the system. Other ways that we use solids concentrations are to describe the removal efficiency, like the removal of suspended solids in primary treatment. All right, so many different ways to represent wastewater solids concentrations. We also have oxygen demand as another major constituent that is quantified in wastewater. So there's two different types of oxygen demand that are used in practice. The first is chemical oxygen demand, or COD. This is the amount of oxygen required to chemically oxidize all organic matter. It's determined using an experiment where a strong oxidant is applied to the wastewater or a diluted version of the wastewater, and then we measure a corresponding color change, which is proportional to the amount of organic matter that reacts. The biochemical oxygen demand, or BOD, is also used to represent organic matter. However, it's used only to represent that portion of the organic matter that is easily degraded or oxidized by bacteria. This is determined by biological experiments, like you see here in these BOD jars. We measure oxygen before and after a period of 5 days to determine how much of the oxygen was consumed, and the amount of oxygen consumed is proportional to the amount of organic matter that's oxidized. We can also calculate the theoretical oxygen demand of constituents where we know the stoichiometry in the relationship. This is not used too much in practice, unless it were a very specific case like an industrial wastewater that has very specific chemical constituents that we can characterize based on their chemical formulas. So this stoichiometry is showing what happens in the biochemical oxygen demand measurement. So we've got this organic matter, which could be anything that's in wastewater: sugars, carbohydrates, etc., which have carbon, hydrogen, and oxygen, as well as other elements. And those are oxidized under the presence of oxygen by bacteria, which also utilize nitrogen and phosphorus compounds to produce new biomass and to oxidize that organic molecule into CO2, into its most reduced form. As a byproduct, they also produce water in this reaction. So we've got the organic compounds represented here in the stoichiometry. We've got the microorganisms, or the microbial biomass. This is represented here in this stoichiometry, and this would be just kind of a representative proportion of carbon to hydrogen to oxygen to nitrogen and phosphorus that you might see for bacteria. We've got dissolved oxygen shown here in the stoichiometry. And in the lab, we're measuring dissolved oxygen after a period of 5 days. We're measuring how much it changes by, and that allows us to know proportionally how much organic content was in the wastewater to begin with, which can be degraded in 5 days. All right, so it's a 5-day test. We usually use the subscript BOD5 to distinguish BOD5 from BOD ultimate, which would be if we were to have run the test for a much longer period of time. The chemical oxygen demand, as I mentioned, is how much organic matter is chemically oxidized using dichromate. So this is also done in a lab at a temperature of 150 degrees Celsius for a couple hours, and it produces chromium compounds that result in color change that can be measured using spectrophotometry. So that color change is proportional to the amount of organic matter that reacts with the dichromate. So we've got the organic compounds, we've got the dichromate, and we measure the colorimetric change associated with the transformation of that dichromate in this reaction. The BOD test again, is done using these BOD jars. We add the wastewater or a diluted version of the wastewater to the jar, and then we shake it to saturate with dissolved oxygen. We top it off so that there's no way for air to get into this jar. And then we let it sit for 5 days and we measure the dissolved oxygen after a period of 5 days. The decrease in dissolved oxygen with respect to the volume of the sample would be used to calculate the BOD concentration. So we measure the BOD at time t equals 0. We cap the jars, we incubate them for 5 days. After 5 days, we measure the DO again, and then we calculate the BOD using the following equation, where P is the decimal volumetric fraction. In other words, it's the dilution fraction of the wastewater in the jar. All right, so the BOD will continue to increase until it finally plateaus, but this happens over a much longer period of time. We conduct the test at a standard time of 5 days. So it's important to note that if you're talking about the total amount of organic material expressed in the terms of BOD, that number should actually be higher than the BOD concentration that's measured in the lab, which is BOD over a period of 5 days. The units of BOD, however, are milligrams per liter, just like the units for COD, and we can use this as a surrogate measurement for, again, the concentration of organic matter in the wastewater. It's also important to note that some microorganisms in the wastewater also oxidize NH3, ammonia nitrogen, so that will also consume some of the oxygen in an experiment. However, it's not, like in the previous example, this is not a surrogate measurement for organic matter, because you can see this particular microbial group utilizes inorganic form of nitrogen as the energy source. All right, so you've got the inorganic energy source, you've got a carbon source because these microorganisms need to fix carbon in order to replicate, and they produce a microbial biomass. They also present a demand for dissolved oxygen. Normally, with domestic sewage and the 5-day BOD test, this is not anything to be concerned about because the increase in the oxygen consumption associated with these microorganisms will typically happen after the BOD test has been completed, because these microorganisms grow a little bit slower. There's a little bit of a lag time before you start to actually see a measurable decrease in the dissolved oxygen concentration due to their microbial activity. All right, but if we had some kind of industrial wastewater, or if we're conducting a test that lasts a longer period of time, we would have to consider the fact that the oxygen depletion might represent not only the carbonaceous demand of carbonaceous energy sources, but also the nitrogenous demand of oxygen due to these inorganic forms of nitrogen. All right, and we can distinguish BOD5 from BOD ultimate. We can also relate that to the COD, where COD is always going to be higher than BOD because there's always some fraction of the wastewater that is not biochemically degradable, but it can be oxidized chemically. All right, and again, we can calculate the theoretical oxygen demand if we have a particular constituent. Let's say it's an organic molecule with the formula CnHaObNc. Depending on the relative contribution of these different elements in the molecule, that would determine how much oxygen, how many moles of oxygen in relation to how many moles of that constituent, which we could use in the stoichiometry to determine the oxygen demand. All right, so let's see an example here. Let's suppose that we're dealing with ethanol. We want to know what is the oxygen demand of ethanol in a wastewater source. So the first step is to balance the chemical reaction and then use that balanced stoichiometry to calculate the theoretical demand of oxygen from the wastewater. So let's suppose that the wastewater has 250 milligrams per liter of ethanol. All right, so we've got our master equation for determining the oxidation of a given constituent based to develop a balanced stoichiometry. as you can see here. So we just need to determine what the values are for N, A, B, and C, and then calculate the coefficients here of the stoichiometric equation using those values. So we can see here for the example of ethanol, C2H6O, we've got N equals 2, A is equal to 6, B is equal to 1. We don't have any nitrogen, so C is equal to 0. So the first one to calculate here, N plus A over 4 minus B over 2 minus 3C over 4. That is 2 plus 6 over 4 minus 1 over 2 minus 0. That's equal to 3. The second one for H2O would just be A over 2, 6 over 2 minus 0. So that's equal to 3 as well. The other ones are just N and C, so that's pretty easy. So we've got our balanced stoichiometry comes out to C2H6O plus 3O2 getting oxidized to 2 CO2s plus 3 H2O, and there's no ammonia, so we just leave it at that. Now that we have our balanced stoichiometry for the oxidation of ethanol, we can calculate the theoretical oxygen demand for a wastewater source with 250 milligrams per liter of ethanol. All right, so first we need the molecular weight of ethanol. So that is equal to 46 grams per mole. And we're going to look at the molar relationship between ethanol and oxygen, and then we'll need the molecular weight of oxygen. So the molecular weight of O2 is equal to 32 grams per mole. So now we just set up our equation, making sure that we convert units appropriately. So if we've got 250 milligrams per liter of the ethanol, we're going to multiply that by, we need milligrams on the bottom, so it's millimole on the top per milligram. And we've got in 1 millimole, we've got 46 milligrams. That's for ethanol. So now we have 1 millimole of ethanol per 3 millimoles of O2 based on our stoichiometry. And then finally we've got 32 milligrams of O2 for every 1 millimole of O2. Millimoles of O2 cancel out, millimoles of ethanol cancel out, milligrams cancel out of ethanol, and we're left with milligrams of O2 per liter. So if we calculate that, it should give us a value of 522 approximately milligrams per liter of O2. This would be our theoretical oxygen demand. So if we were to take the COD, using a laboratory experiment, calculate the COD of this wastewater sample, 250 milligrams per liter of ethanol, we should get approximately 522 milligrams per liter COD as well. All right, we also have industrial wastewater, and industrial wastewater has a high strength compared to domestic wastewater. Industrial uses produce a wastewater that's very different in composition from domestic wastewater. And because there may be some chemicals that could inhibit some of the microbial action that we rely on in the centralized treatment plant, often industrial wastewater facility or industrial facilities that are producing wastewater are required to provide some level of pre-treatment before they discharge their sewage into the collection system. So this helps reduce the wastewater strength. It may help also dilute the wastewater, equalize some of the flow, and importantly also remove some of the toxic constituents like metal ions, which could interfere with the wastewater treatment processes downstream. All right, so this table right here just shows some typical BOD, COD, solids concentrations, etc., for 3 different wastewaters from 3 different industries. Let's do an example problem using the values from the tables shown. What is the population equivalent for meat processing wastewater? So in other words, how many people would it take to generate wastewater with an equivalent flow rate? All right, so the concept of person equivalence is used frequently in wastewater treatment to indicate the relative strength of a facility, such as an industrial facility or a wastewater source coming from some other location that's not residential. So it's to convert whatever that wastewater source, its characteristics, to convert that into an equivalent population if it were domestic wastewater. So remember, for domestic wastewater, we have kind of a typical per capita flow rate. It could be between 80 to 120 gallons per person per day, pretty typical values. For this example, let's just assume 120 gallons per person per day. And that wastewater has typical strength. For example, the BOD concentration is typically about 200 milligrams per liter, TSS concentration about 240 milligrams per liter. And we can also characterize a typical loading that would come from a residential unit per person per day. If you need a refresher on that, you can take a look back at examples 3.1 and 3.2 of this module. So from those examples, we calculated that the BOD loading, based on a concentration of 200 milligrams per liter, and this per capita flow rate, the loading is about 0.20 pounds per day per person. And for TSS, suspended solids, for a typical concentration of 240 milligrams per liter, and assuming the per capita flow rate of 120 gallons per person per day, we found that the per capita loading was approximately 0.24 pounds per day per person. So now, in this example problem, we've got some data about a meat processing facility, and we're being asked to determine the population equivalent for its flow rate and for its BOD and TSS concentrations. So we can think about this kind of like a comparison, set up a table. We've got the flow rate here. We've got the BOD concentrations, and we've got the TSS concentrations. For the meat processing facility, the flow rate is 1.2 million gallons per day. For one person, our flow rate per person, we're assuming 120 gallons per person per day. All right, so for the flow equivalent, for the person equivalent on a basis of flow rate, it's just taking this value and dividing it by the flow rate for a single person. That gives us a population equivalent of 10,000 people. We can use the units PE for population equivalent. For BOD and TSS, we have to think about this in terms of loadings, because the concentrations are different at the facility than they are at the residential unit. So we have to first look at what information we have in the table about the BOD loading. And we can see in the table that the BOD loading is 13,000 pounds per day. The TSS loading is 9,600 pounds per day. And if you remember from examples 3.1 and 3.2, for an individual person, we estimated again that the BOD and TSS loadings were 0.2 and 0.24 pounds per day per person. So again, for the determination of population equivalent, if we're working on the basis of BOD, we would take 13,000 pounds per day divided by 0.2 pounds per day per person. And that gives us a population equivalent of about 65,000. So what this means is that the BOD strength, the organic strength of this meat processing facility wastewater, is equivalent to the BOD strength of about 65,000 individuals. If we were to look at it by flow rate, the flow rate of the meat processing facility is only equivalent to 10,000 individuals. So clearly you can see here that the meat processing facility produces a higher strength wastewater. Last one is our TSS. So that's the same setup as this BOD situation where we've got a loading of 9,600 pounds per day coming from the facility and 0.24 pounds per day per person. If we divide those numbers, we get 40,000 population equivalent, approximately. All right, so you can determine the population equivalence based on flow rate or based on any constituent for a given facility. All right, now let's talk about an overview of wastewater treatment technologies. So we can characterize or classify wastewater treatment technologies based on two main elements. One is how the microbes are growing, how the microorganisms are going to grow in the system, because wastewater treatment technologies typically rely on microorganisms to complete the treatment. So the first way we can characterize these systems is whether they have suspended growth of microorganisms or attached growth. The second way we can classify wastewater treatment technologies is whether or not oxygen is required. And if oxygen is required, how do the microorganisms get their oxygen? Is it by natural mechanisms or is there forced aeration into the system? All right, so here you have, suspended growth compared with biofilm growth or attached growth. So more common, used in the United States, would be the aerobic biological secondary treatment systems. All right, so in small towns, you might see stabilization ponds or lagoons. These are suspended growth treatment systems that require oxygen and utilize natural mechanisms to aerate the wastewater, usually the production of oxygen by algae that are naturally present in the ponds. Trickling filters are another natural aeration process, however, uses attached growth rather than suspended growth. So in trickling filters, the microorganisms attach onto a media surface, in some cases rocks, in other cases plastic media, and so they grow attached to those surfaces in biofilms rather than suspended in the wastewater itself. Conventional activated sludge system uses suspended growth in a forced aeration system, and then other technologies like rotating biological contactors also used for forced aeration, but they use an attached growth process. There's also a whole class of anaerobic biological wastewater treatment technologies, and these are mostly tend to be attached growth. They also tend to require high COD concentrations in the influent. They're not so common in the United States. However, they are common in some other countries, especially in Brazil and Latin American countries. In some small communities in the US, you might see anaerobic biological treatment systems. And if you talk about at the household level, then the septic tank is another example of an anaerobic treatment system for wastewater produced at the household. So anaerobic baffled reactor is one type of system that's used, which is anaerobic and it's biological. So this would be an example, would be like the improved septic tank, which has a series of baffles to encourage less sludge production and better performance in some cases. The anaerobic filter is kind of like a trickling filter, except it's anaerobic, and the wastewater flows upward usually through the filter in the absence of oxygen. So you get different communities of microorganisms rather than microorganisms that need oxygen as a terminal electron acceptor to oxidize that organic matter, convert it down to CO2. You get different groups of fermenting microorganisms, acidogenic microorganisms and acetogenic microorganisms, as well as methanogenic microorganisms, which are oxidizing that organic matter down to methane, CH4, and also some CH2. Another technology used, especially in tropical climate countries like Brazil, parts of India, this technology has become very popular, the upflow anaerobic sludge blanket reactor. So this utilizes anaerobic treatment process with attached growth on sludge granules. All right, so let's go through some of these technologies and see what they look like, and also talk a little bit about their characteristics. So the activated sludge technology is one of the most common used in the United States, especially in larger cities. In this system, we've got primary effluent, or in some cases raw wastewater, which is discharged to an aeration basin where you've got air being pumped into the bottom and bubbled up into the wastewater using diffusers. That air contains oxygen. The oxygen is used by the microorganisms to degrade the organic matter. All right, so you get incredible microbial growth in this system. You get what we call a mixed liquor, which is highly turbid product where you've got lots of microorganisms that have grown in the tank by degrading the organic matter present in the sewage. So usually the effluent of the aeration basin gets discharged to a clarifier, which you see here, like these sedimentation tanks, where we separate out the activated sludge or the active biomass. And some of that gets wasted and some of it gets returned back to the beginning of the system so that we can maintain some of the biological growth that has become acclimated to the system and is highly active. All right, so this is a typical activated sludge system. When we talk about typical treatment processes for larger cities in the US, conventional biological processes would usually look like this. You've got preliminary treatment consisting of screening, comminution, grit removal, equalization in some cases, and also primary settling. This would be part of primary treatment. So you've got preliminary and primary treatment to remove heavier, larger, easily settable materials and materials that are large enough to screen out of the wastewater. That would be accomplished during preliminary and primary treatment. So in primary, you'd have some settling to get rid of the primary sludge, some of the heavier solids that might be present in the sewage. Secondary treatment, again, uses, for a typical treatment process in urban centers of the United States, secondary treatment would typically consist of an aerobic basin, an aeration basin, followed by secondary settling, where you get the separation of the secondary effluent and the waste activated sludge, some of which is returned. Tertiary treatment is not seen in all systems, but in some systems, especially where the discharge requirements are more stringent for things like nutrients, or in other cases where the water is intended for reuse and it needs to be of higher quality, we might have tertiary treatment systems, which usually consist of filtration followed by some type of disinfection. All right, so if we have tertiary treatment, we would call that tertiary effluent. If we only have secondary treatment, we would call that secondary effluent. And of course, primary settling produces primary effluent. All right, so another variation on this type of biological treatment process is what we might do in the case where we need to achieve lower total nitrogen concentrations. Okay, so based on what you know about the nitrogen cycle, you know that if it's excreted in the form of ammonia nitrogen or urea, for example, and it rapidly decays into ammonia nitrogen, that ammonia can be converted to nitrate in an aerobic environment. So if we have aerobic treatment here, we would have that conversion from ammonia nitrogen to nitrate. In order to convert nitrate into nitrogen gas, we need to have an anoxic or an anaerobic environment so that we can get methanogens to come in and degrade some of the remaining organic material, and they use, in the absence of oxygen, those organisms would use nitrate as a reduction for reducing power. So they would use the nitrate kind of to breathe, in a sense. Instead of using oxygen, because they're in an anaerobic environment, they would use the nitrate. That nitrate would get converted to nitrogen gas, which allows it to re-enter the atmosphere. All right, so in these systems, you would have the aerobic treatment followed by an internal recycle, which brings back that nitrate back to the beginning of an anaerobic tank, where you would get the denitrification to occur. So if you have this type of system, you can not only do you get BOD removal in the aerobic aeration tank, but you also get some nitrogen conversion, nitrification, and followed by denitrification. All right, to achieve that conversion of nitrogen, you would need both aerobic treatment followed by anoxic treatment. An important constituent that needs to be present for denitrification is an organic material, right? We need, those microorganisms are using the nitrate as their oxygen source, but they are degrading some organic molecule. So either that organic compound has to be added back into the wastewater, or if you have this internal recycle, the organic matter in the wastewater itself can serve as that energy source for those microorganisms which are denitrifying. Okay, so here you can see that the secondary treated wastewater would still typically go through some type of tertiary treatment process, followed by disinfection before being discharged in the environment or maybe being reused for some purpose. In some systems where potable reuse is the end destination of the wastewater, after tertiary treatment, we would have an additional series of treatment processes, which are typically referred to as advanced treatment and purification. So advanced treatment processes look different in different systems, but one typical treatment train is membrane filtration, followed by cartridge filtration with reverse osmosis to remove essentially everything from the water. After that, hydrogen peroxide, advanced oxidation, disinfection would be used to get rid of any remaining pathogens that might be present in the water. And then after that, water conditioning, like the decarbonation, the addition of lime contact chamber to put back some of the ions into the water, which were removed in the reverse osmosis stage. So this is one example of an advanced treatment process. Other advanced treatment processes might use ozonation up front, right after tertiary treatment, followed by some kind of biological activated carbon filtration. And then after that, you'd see the membrane filtration, reverse osmosis, advanced oxidation processes that you see here. All right, so this would produce a water product which is purified and could be ready for direct consumption, or in some cases might be discharged back to the environment, mixed or blended with some other raw water source, and then used as raw water for a potable water treatment plant. So you get several different stages of treatment in the advanced treatment process. All wastewater treatment processes also produce some type of sludge byproduct. So the sludge essentially consists of microbial biomass, and some systems might produce more sludge than others, like activated sludge produces a much higher volume of waste sludge compared to anaerobic treatment processes and compared to some on-site treatment processes like septic tanks or baffled reactors. But all treatment processes produce some type of sludge. All right, so the sludge needs to be managed because it, first of all, could contain pathogens, so it could be harmful to handle if it's not treated appropriately. And second of all, the sludge is not really stabilized when it gets collected from wastewater treatment process. It could create noxious odors and other concerns when it starts to degrade. So the third problem with sludge is that it's very high in water content, and therefore it's very heavy and very voluminous, meaning that we need to do some processes, we need to utilize some processes that remove the water and reduce the volume of the sludge so that they can more efficiently be transported to a different location where they might be reused, let's say in soil amendment or in some type of agricultural application. So typical treatment process for sludge is to thicken the sludge first to remove some of the water from the sludge, then to send it to some type of treatment process like an anaerobic digester, which would produce biogas using the same communities of microbes as anaerobic wastewater treatment processes. Following anaerobic digestion, we would then further remove some of the water by dewatering. We might add polymers to condition the sludge a bit more and make it more stable. And then finally, the biosolids are what's referred to as the final treated product of sludge, which can be reused or returned to the environment. The water, which is squeezed out from thickening processes and dewatering processes, needs to be either treated or returned back to the headworks of the treatment process. All right, in small systems, different technologies are used. So again, activated sludge is very commonly seen in large cities in the US, but smaller towns and smaller cities throughout the world, including the US, utilize different technologies like some of the ones that you see here. Stabilization ponds, which include different types of ponds like anaerobic ponds, facultative ponds, maturation ponds. Biological reactors in some cases are used, like anaerobic reactors in combination with ponds, or various variations of this technology, like the aerated pond. All right, so we have, in terms of the number of facilities in the US, there's actually quite a few that utilize these small flow treatment processes. However, in terms of volume, the amount of liters or gallons of wastewater treated per day, it's actually a very small percentage. So this is an example of what a stabilization pond system looks like. You can see it's really just an excavated basin where you have sunlight hitting the wastewater, and the wastewater stays in there for a long period of time, many days, maybe even weeks or months in some case. During that time, the sunlight allows for the growth of algae. The algae are utilizing the nutrients that are naturally present in the wastewater and the energy from the sunlight. So in this pond here on the left, you can actually see that the color of the wastewater changes to a green color, and that's because of all the algae growth. So those algae in turn, they are producing oxygen as a byproduct, and that oxygen becomes a source of reducing power for the bacteria in the wastewater that are degrading organic matter. So kind of similar to what you see in the activated sludge system, where the oxygen is pumped into the wastewater so that the bacteria are able to degrade and convert those organic molecules down to CO2. You get some of that same activity in stabilization ponds, only it happens a lot slower because we're relying on the algae to kind of pump oxygen into the wastewater. Oxygen will also diffuse into the wastewater just based on the large surface area and the fact that oxygen is present in the atmosphere. All right, so there's two examples of stabilization pond systems. Trickling filters are also another technology that are utilized in small towns and small cities and places outside of the United States. So here's an example of a trickling filter system that is at a demonstration plant in Tijuana, Mexico. You can see it's basically a large tower. Inside this tower, there's a bed of media. Again, the media could be stones, could be rock, could be some type of plastic media. The important thing is that it has a large surface area where microbes can develop biofilms and start to grow. So that as the wastewater gets sprinkled through and trickled down through this media, those bacteria are there to break down the organic matter present in the wastewater. And because it's kind of trickling down, the air has an opportunity to flow in through the system. And so it gets kind of like a natural aeration rather than having to run aeration pumps, like is the case in the activated sludge system. All right, so another example of a small flows treatment system that is used in different contexts. The rotating biological contactor, again, this is a forced aeration system, kind of like activated sludge. However, the difference is that instead of developing microbes that are growing in suspended growth, this system is optimized for the growth of microorganisms that form biofilms as attached growth. So you have these large rotating wheels, and on the wheels there are some type of media, which again provides that surface area for the microbes to attach to, and they form that kind of biofilm slime that you would see on any substance that's in contact with wastewater. Those microbes then are being cycled through the water. They're being brought out into the atmosphere where they get re-aerated and back into the wastewater, where they're in contact with the organic material, and they're able to degrade that organic material down to CO2. Anaerobic baffled reactor utilizes different types of microbial communities that don't need oxygen. So like fermentating bacteria, acetogenic, acidogenic, and methanogenic bacteria. They're converting in a series of steps that organic molecule is getting broken down into methane and CO2. And the methane can actually be captured and reused as a fuel source, or in some cases might just escape into the atmosphere. But the baffled reactor utilizes a series of baffles to continuously bring that wastewater into contact with settled sludge, where you have large communities of microorganisms in kind of like a sludge blanket. So that allows more efficient contact of the microorganisms with the wastewater, and you get higher efficiency of treatment in anaerobic baffled reactor compared to, let's say, like a septic tank. The anaerobic filter uses a similar concept, attached growth. However, in this case, the media are added to the reactor, and you just pass the wastewater up through the media and out the effluent. So while it's passing through this layer of media, the microorganisms that are attached to the rocks or to the media, they are able to break down the organic matter from the wastewater into methane and CO2. The UASB reactor is a little bit similar to the anaerobic baffled reactor in the sense that the influent wastewater is brought in from the bottom of the reactor, and it passes up through a heavy sludge blanket layer where you've got communities of microorganisms, communities of bacteria that are breaking down the organic content in the wastewater into CO2 and methane, which can, in this particular type of reactor, it's built with a process to capture that biogas and be able to use it as a fuel source. So this type of treatment technology is very common in warm climates for secondary wastewater treatment. And here's an example of a system in Brazil that tests out different variations of the design of UASB reactors. They're used in full scale in Brazil in a number of different treatment plants. So getting back to lagoons or stabilization ponds, this is maybe one of the more simple wastewater treatment technologies. It's very simple to construct. It's very easy to maintain. It does take up a lot of land area, but it possibly is the most common wastewater treatment technology in the world. In particular, again, for small towns, rural communities where available land is not an issue, people are not crowded too closely together, and the availability of that land might be worth the trade-off in how simple the system is to operate and maintain. All right, so in the US, according to the US EPA, as of approximately 2000, the year 2000, there were more than 8,000 domestic wastewater treatment ponds in the US, which is more than half of the permitted facilities. So again, this is a technology that's very common in terms of the number of treatment plants, but they're used in small flow systems. So they're not talked about too much in the literature. We don't focus too much on their design in this class, but I do want you all to understand that these systems exist and they're very common, especially in small towns and in other countries as well. And this is just a map showing the location of all the pond systems in the US according to the EPA database as of the year 2000. So here's some examples of these stabilization pond systems. You can see this one in Maine utilizes the effluent of the pond to irrigate a series of what looks to be maybe trees, could be for lumber production. So you can kind of combine these natural wastewater treatment processes with water reuse to make that treated effluent into a resource rather than a liability that has to be discharged back into a river, right? So you can land apply the effluent and make some productive use out of the nutrients in that treated wastewater. Here's another example of a stabilization pond system in Florida that was used for treating wastewater of a correctional institute, and the effluent here was used for irrigation of some crops nearby that produced something useful, a useful output that could be used in the facility itself. Here's another example of a small town in Missouri. You can see that, small population center. They have plenty of available land, and the wastewater treatment plant consisting of stabilization ponds is located far enough away from the population center that it doesn't create any issues in terms of odor for the nearby population. Right? So you would not use one of these systems in a densely populated urban community where you would have households very close by, because being an open system to the atmosphere, it does can tend to produce odor issues once in a while. And however, a well-operating, a well-designed system with a sufficient capacity would usually not even produce very strong odors, even if you were right on site. All right, so you'll see these systems in small towns. However, they're commonly being replaced by mechanized systems, and that may or may not be a good thing, depending on the situation, right? So these systems are very low cost to maintain, and they're more sustainable in terms of energy consumption. Here's a good example that I like to show in Argentina. So this is the city of Mendoza, has a series of pond systems used to treat some of the wastewater from the urban center, and you can see they locate it fairly far away from the urban center, so you still have it away from the population. But the effluent here is being reused to treat, or being reused to irrigate grapevines that are used for wine production. And if you're familiar with Mendoza, you know that it's a wine producing region. It's very productive in terms of high quality wine products. So it's an example here of using wastewater reuse with a natural system to convert wastewater into wine, essentially. All right, so when you think of wastewater treatment system design, you want to think of sustainability as one of the priorities, right? So utilizing systems that are low energy or that produce some type of biogas or energy that can be recovered and reused, or maybe produce a treated effluent that can be reused to offset water demands for a certain region, and just that suit the needs of the population. So here's an example of a stabilization pond system in India that was used to serve a smaller town, and that smaller town grew into a larger city as industrialization happened. And so the original pond system was replaced with a system that had a combination of smaller footprint reactors combined with polishing ponds. And this has been the case in some towns in the United States too. Like here's an example of a town that used natural wastewater treatment system with stabilization ponds. And over time, you can see that the system became more and more mechanized. All right, so you see this very common in small towns, is the replacement of natural wastewater treatment systems into smaller footprint mechanized systems. So here's a topic for discussion. I want you to think about the difference between natural wastewater treatment technologies and mechanized systems. All right, so what do you think are some of the advantages, and what do you think are some of the disadvantages of these different types of technologies? What are some of the trade-offs that might be associated with converting a natural wastewater treatment plant into one that's more mechanized. All right, the next topic in this lecture is preliminary and primary treatment. So our learning objectives for this part of the lecture are to calculate flow rates using a partial flume, to determine the effect of flow equalization on constituent loadings, to describe the types of screens that are used in treatment plant headworks, and to calculate the head loss and flow velocity through a screen, to design an aerated and vortex grit chamber, and to size a clarifier based on the detention time, the overflow rate, the scouring velocity, and typical dimensions. All right, so as an overview, if we look at the centralized wastewater treatment process, and we talked a little bit about small flow systems, but for the rest of the semester, we're going to be focusing on the design of biological treatment systems like activated sludge and the variations of activated sludge. So in a typical conventional biological treatment system, you would have preliminary and primary treatment. So preliminary treatment being also referred to as the headworks, primary treatment usually consisting of settling. After preliminary and primary, you've got secondary treatment, where you've got an aeration basin, like biological treatment in the aeration basin, followed by secondary settling. Then you've got tertiary treatment and disinfection in some cases to produce the final liquid effluent. And then you've got sludge management. So the sludge produced in the secondary treatment, the sludge produced in the primary treatment, and also in some cases, some solids that are produced in preliminary treatment. Those are collected, they're combined, they're thickened and treated in order to stabilize that sludge into a biosolid material that can be disposed of or reused safely. All right, so right now we're going to be focusing on this first part, preliminary and primary treatment technologies. So let's see an overview of preliminary treatment, or the headworks. You've got flow measurement, flow equalization, screening, pumping, which we're not going to cover in this class, and grit removal. These are the processes that you'll find at the headworks. Typical arrangements of preliminary treatment in municipal wastewater treatment plants. You see the lower sequence here. This is more common in smaller plants. The sequence up here on top is more common in larger facilities. So in the larger facilities, you might have raw wastewater pass through a partial flume, where you can take advantage of recording and measuring flow rates. After that, it would go through a mechanically cleaned bar screen to remove the larger substances that come into the sewage. And after that, you might have a pump station, followed by vortex grit chambers, where the grit is removed, the heavier settleable grit, and the effluent from those vortex grit chambers would go to primary treatment. In a smaller system, a little bit different configuration, you might have the raw wastewater being first screened using maybe, as opposed to mechanically cleaned screens, you might have screens that are cleaned by hand. So after that, you'd have a partial flume. This helps stabilize that screen, the level of water in that screen. And also you can take advantage of measuring the flow rate in the partial flume. You might then have, again, a pumping station here, followed by grit chambers. In this case, maybe aerated grit chambers rather than vortex grit chambers. And then the effluent of the grit goes again to primary treatment. So these images here on the lower left, this shows you a mechanically cleaned bar screen. So this is to remove the larger substances so that they don't damage downstream processes. And then you can see here an aerated grit tank, which is removing some of the scum and grit that comes in the sewage. Flow measurement occurs, again, usually at the headworks in a partial flume. So all wastewater treatment plants in the United States are required to monitor flow rates. And the devices that are normally used to measure flow include the partial flume, in some cases with an automatic flow recorder. And another technology used is magnetic flow meters. This can be installed in the discharge piping from the influent pump station. But the partial flume is the most ideal method. This is a plan view of what a partial flume looks like, and a profile view. So you kind of see that you've got this geometry which creates a bottleneck in the channel, in an open channel. And at the same time, at that bottleneck, which has a width of B, you also get a drop in the elevation, which causes this kind of like standing wave, the water surface to drop down and then come back up. So the flow rate, and this is a very specific geometry. So these devices they're produced in a factory, and they're purchased by the treatment plant and installed. They're brought to site and then installed in a channel. So they have to be machined and fabricated to the exact dimensions that are required. But once you have a partial flume and you have a steady flow rate coming up to that flume, you can relate the flow rate to the height of the water in a stilling well upstream from the hydraulic jump. And you could also relate it to the width of the throat. So if you know the dimensions of your partial flume, and if you're able to measure the height of the water upstream of the partial flume, then you can calculate the flow rate in cubic feet per second using this equation. All right, so that can be that height can be continuously monitored using technology that would allow you to get continuous flow readings in wastewater treatment plant. All right, let's do an example problem. So calculate the hourly flow rates for a wastewater treatment plant using a partial flume with a throat width of 4 feet based on the following depth measurements in the upstream stilling well, and round your answers to the nearest 0.1 cubic feet per second. Okay, so to calculate the flow rate based on the depth and throat width of a partial flume, we've got the equation Q is equal to 4 times B times H raised to the 1.522 B raised to the 0.026. So important. This is obviously an empirical equation. The important thing to consider here are the units. And so B here, the units are in feet. H here, the units are also in feet. And this gives a Q value in cubic feet per second. All right, so based on the data we have, the throat width B is equal to 4 feet. And the depth of the water upstream of the partial flume is changing throughout the day. I'll do an example calculation for the first two measurements, so 8.7 inches and 4.3 inches. First thing we need to do here is convert this to feet. So this is approximately 0.73 feet, and 4.3 inches approximately 0.36 feet. So then we just implement the equation. So Q for the 8.7 inches reading is equal to 4 times 4 times 0.73 raised to the 1.522 times 4 raised to the 0.026. And that gives a value of 9.7 cubic feet per second. If we do the same thing for the 4.3 inch reading, that gives us a value of approximately 3.2. All right, and you can see here's a solution to that example problem. So you can see the corresponding flow rates with each of the depths that were measured at different times during the day. One of the other processes that's commonly found in the headworks is flow equalization. Flow equalization is essentially a storage tank where the sewage comes in and is discharged at a constant rate. So it comes in at variable rates. Again, there's peaking periods throughout the day where you might have very high flow rates coming into the system and then lower flow rates during the night. The equalization tank is there to kind of stabilize those flow rates so that you can store sewage when the flow rates are higher. You have the ability to store sewage and then it can empty out during the evening when the flow rates are lower. So having a constant flow rate discharged from your equalization tank allows your primary clarifier, your secondary treatment system to have more consistent conditions, less fluctuation in the flow rates, also less fluctuation in the loadings of organic matter. And this just helps the system perform better, perform more consistently. So you eliminate the chance of any types of shock loadings, which could decrease the efficiency of biological treatment. You also dilute some of the inhibiting substances, which might be found, especially if you have industrial wastewaters mixed in with the system. You're stabilizing the pH, so you're providing kind of more stable conditions for those bacteria to thrive. The effluent quality is improved, again, because of this consistency that you're introducing into the system. So of course, this is an additional cost. It's an added space that has to be accounted for at the treatment facility. You would need a, considerably large tank in order to equalize the flow rate for an entire day. But the benefits from including flow equalization may outweigh some of those costs. So here's an example of a plot that shows the cumulative inflow volume. So throughout the day, you can see that the average daily flow rate is accumulating in the tank. And it has this curve, which is characteristic of the fluctuating flow rates throughout the day. If you draw a straight line from the beginning of that flow curve to the end of the flow curve over a 24-hour period, and then you draw a line parallel to that line, which is exactly adjacent to, just touches the edge of the curve there, then you can calculate the required equalization volume based on the height between those 2 points. All right, and the curve might be different. In this case, it's an S-shaped curve. In the case here on the right, it's more of a bowed curve. But either way, the equalization volume is calculated by taking the vertical distance between those two extreme points. Let's do an example problem to see how this works out. All right, so for the flow rate data given in the following table, I want you to determine the storage volume required to equalize this flow rate. And then once you determine the required storage volume, find out what effect that flow equalization will have on the BOD mass loading rate coming into the treatment plant. So you've got the average flow rate during each time period, so midnight to 1 a.m., 1 a.m. to 2 a.m., 2 to 3, etc. And for each of these flow rate, you also have an average BOD concentration. So you can see that not only does the flow rate fluctuate, but also BOD concentrations coming into the system will fluctuate. And you tend to have higher BOD concentrations when you have higher flow rates. So that just makes the equalization, even more impactful in terms of stabilizing the mass loading of constituents. All right, and here you can see the solution for that example problem, which is step by step. First, to determine the volume of the basin for flow equalization, develop a cumulative volume curve. You obtain that by converting the average flow rate during each hourly period to cubic meters using the expression shown here below. And then you sum those hourly values to obtain the cumulative flow volume. All right, so here's an example for the time period midnight to 1 a.m. We've got a flow rate of 0.275 cubic meters per second. Convert that to cubic meters per hour, and then we multiply it by 1 hour because we're dealing with the time period from midnight to 1 a.m., which has a duration of 1 hour. That gives us a value of 990 cubic meters, which is the total volume of sewage that would come into the treatment plant during that hour from midnight to 1 a.m. We do that again for the time period 1 a.m. to 2 a.m., 0.22 cubic meters per second, multiplied by that hour, converting the units here, we get a value of 792 meters cubed. All right, so the cumulative flow expressed in cubic meters at the end of that time period 1 a.m. to 2 a.m. would be the 990 cubic meters from the first hour plus the 792 cubic meters from the second hour, equals 1,782 cubic meters. All right, so we can do that for all 24 hours in the day, and we would get the values shown here in the table on on the right. So you could see that 990 cubic meters followed by the 1,782. And then you just keep adding up the hourly accumulation for each hour until we get the total value here at the bottom, 26,550 cubic meters. And that would be over the course of a 24-hour day, the total volume of sewage that would be received at the plant. All right, if we divided that volume by the number of seconds in a day, we would get the average flow rate during that day, which is 0.307 cubic meters per second. The next step is to prepare a plot of the cumulative flow volume as shown in the diagram that you'll see in a second. So the slope of the line drawn from the origin to the endpoint of the inflow mass diagram is the same thing as the average flow rate for the day, which, as you saw in the previous slide, is equal to 0.307 cubic meters per second. All right, so the next step is to determine the required storage volume. So this is found by drawing a parallel line to the average flow rate, which is tangent to the low point in the mass diagram, and then look at the vertical distance between that tangent point and the straight line that connected the cumulative volume at the beginning of the period to the end of the period. All right, so as you can see here in this plot below, and this is the situation where we have kind of a bowed shape in our curve. We connect the midnight 00 point to the midnight point here at 24 hours and 26,000, approximately 26,000 cubic meters of cumulative volume. We draw a we draw a straight line between here and there. That's the average flow rate throughout the day. And then we draw a parallel line to that line at the tangent to the curve at the lowest point in the curve. And then that difference between this tangent point and the parallel line is the equalization volume, which in this case, you can see the distance here is 4,110 cubic meters. So that's basically how big our tank needs to be. Step 2 is to determine the effect of the equalization basin on the mass loading rate. Okay, so we know that the equalization basin is going to completely smooth out the flow rate leaving the basin, right? Instead of discharging these fluctuating flow rates that go from 0.105 or 0.1 cubic meters per second to as high as like 0.43 cubic meters per second, we are now discharging a constant 0.307 cubic meters per second throughout the day because we have that ability to store in the equalization basin. But what effect does that have on the BOD loadings coming into the system? All right, so first step to do this is to compute the liquid volume in the equalization basin at the end of each time period throughout the day. So we do this by subtracting the equalized hourly flow rate expressed as a volume from the inflow flow rate expressed as a volume. So using the example from the previous table, we can see that the volume corresponding to the equalized flow rate for a period of 1 hour is we take that average flow rate, 0.307 cubic meters per second, convert that to cubic meters per hour, and multiply that by 1 hour. We get a volume of 1,106 cubic meters. So that's how much volume is being discharged from the tank during every hour. And then we use this value to compute the volume in storage using this expression here. All right, so as an example, we take the volume starting. So let's say, we're starting with the tank completely empty, and we know that it's completely empty at about 8:30, and we know that because that's kind of the inflection point of our curve in the previous slide. All right, so the time period from 8 to 9, we're starting with a volume of 0. To that, we're adding 1,278 cubic meters. That's as shown, by the calculations we did here previously. So from 8 to 9, the difference in that cumulative volume is 1,278 cubic meters. Then we're subtracting from that the constant flow rate that we're pumping out of the system, the 1,106 cubic meters that you can see we calculated up here. All right, so you can see here we are receiving more from that hour. We're receiving more sewage into the equalization tank than what we're discharging. So we're going to get an increase in the level of sewage in the tank. All right, and that increase between that 1 hour period, it's going to increase by 172 cubic meters. We can do that calculation again from 9 to 10. All right, so we have 172 cubic meters in the tank based on our previous calculation. That's what we're starting out with. To that, we're going to add the volume of sewage that's received at the equalization tank from the hours of 9 to 10. That's 1,476 cubic meters. And then we're going to subtract what's being discharged from the tank, which is a constant 1,106 cubic meters. That's not going to change again, assuming we're pumping out 24 hours a day, right? So if we perform this calculation, we get a value of 542 cubic meters. So after that first 2 hours, the volume in the tank increases to 542 cubic meters. And we repeat that calculation for the rest of the 24-hour day, and we're going to see that level go up. It's going to go up to our maximum storage volume, and then it's going to start to come back down. Because in the middle of the night, we're going to be discharging more sewage than what we're bringing into the system. All right, so we're going to organize all of this in a computation table. And to the table, we're also going to add the calculation of the average concentration of BOD that's leaving the storage basin. So if we assume that when every sewage comes into the basin and everything kind of mixes together while it's in there, we can use the following expression to calculate the concentration of BOD that's leaving the tank, even if it's coming in at different fluctuating concentrations. All right, so for this, we're going to use the concept of loading, mass loading, and concentrations. We know that if we take the concentration of a constituent, let's say BOD, that's represented here by X, and we multiply that concentration by the volume that comes in, represented by V, what we're going to get is a mass. We're going to get milligrams per liter multiplied by liters would be equal to milligrams. So we get a mass of BOD that's coming into the tank. We add that to the mass of BOD that was already in the tank in the previous hour, so from the previous calculation, and then we divide that cumulative mass by the cumulative volume, meaning the volume that was already in the tank and the volume that was just added to the tank in the past hour. So for example, from the time period 8 to 9, we don't have any sewage in the tank, so there's no BOD in there, but we're adding 1,278 cubic meters of sewage, and that sewage has a concentration of 175 grams per cubic meter, which was given in the original table in the original example problem. So that tells us how much BOD we have, mass, in the storage tank, and we divide that by the total volume in the storage tank, which in this case is just equal to 1,278 because we started with a volume of 0, so there was nothing in there to begin with. And you can see this is a very simple calculation. We get back 175 milligrams per liter, but just to demonstrate the method, right? Demonstrate the calculation. Okay, so after time period 8 to 9 at 9 a.m., we've got 175 milligrams per liter. Now let's look at the next hour from 9 to 10. So if you recall from our previous calculation, we found out that after the 8 to 9 hour, we're going to have a total volume of 172 cubic meters of sewage in the tank. All right, so if we take that volume, 172 cubic meters, and we multiply that by the BOD concentration that we just found, 175, that's going to give us the mass of BOD that's already in the tank when we start at 9 o'clock. To that, we're going to add the mass that accumulates between the hours 9 and 10. And then we're going to divide that whole thing by the total volume in the tank. And that's going to give us a concentration of 197 milligrams per liter, or grams per cubic meter. All right, so you can see that from 8 to 9, our concentration is 175. From 9 to 10, it increases to 197. 197 is slightly less than the 200 milligrams per liter that's coming in between the hours of 9 and 10. And that's because that 200 milligrams per liter is getting blended with a lower strength wastewater that's already in there from the previous hour. So that gives us a slightly lower concentration. So you can see the effect of BOD concentrations being dampened as they leave the equalization tank. All right, the third step is to compute the hourly mass loading rate using the following expressions. So we take that 175 milligrams per liter, multiply it by the average flow rate and number of seconds in an hour. Convert that to kilograms. We can see that the mass loading during the period 8 to 9 is 193 kilograms per hour. We repeat these calculations for each hour. We can summarize the results in a table, and we can see the effect of flow equalization by plotting those values with respect to the time of day. All right, so you can see here the values in the table. We've got the volume in storage at the end of the time period, and we're starting with that time period 8 to 9 because that's when our tank is empty. And when it starts to fill up, and then you can see it comes back down to empty by the following day at 7 to 8. We've got that average BOD concentration during each time period. So coming into the tank, 175 followed by 200 and 215. And then we can see the equalized BOD concentration that's leaving the tank, and it's going to be slightly lower than what's coming in. So 175, 197, as we saw in the previous calculation, 210, which is lower than 215, etc. And then we have that equalized BOD mass loading that we calculated. So the 193 kilograms per hour, you can see how that fluctuates throughout the day. All right, so you see in the plot here, what's coming into the tank, right? The normal BOD mass loading, which is shown here in the dotted line, is much higher peaks and lower valleys than the equalized BOD mass loading, which is much more dampened. The flow rate has these big peaks coming up and down. The equalized flow rate, of course, is just a constant rate that we're pumping out of the tank. So the flow rate becomes completely equalized. The BOD concentration, however, also has some equalization, and that helps the stability and the performance of our treatment system downstream. Okay, so let's see how we can set up these calculations in Excel. First thing we want to do after entering the data for the flow rates during each time period is we can calculate the average flow rate. We get 0.307 cubic meters per second. Next thing we want to do is just to clarify that we've got the average flow rate that's coming into the equalization basin at each time period, and then we have the average flow rate that's leaving the basin. And during each time period, that we're going to be pumping the same flow rate of water out of the basin. So it's going to stay a constant 0.307 throughout the day. So we can just drag that down to the bottom, and that just shows us that even though the flow rate is fluctuating in the influent, it's going to be constant at the effluent. Next thing we want to calculate is the volume received during each time period. So that's the total cubic meters of water that enter the basin during each hour. All right, so the way we do that is we calculate the average flow rate multiplied by 60 seconds in a minute and multiplied by 60 minutes in an hour to get the total cubic meters. Next thing we want to do is calculate the volume that's discharged during each time period. So that's going to be the same calculation, just we're taking the flow rate leaving the basin, 0.307, multiplied by 60 seconds in a minute and by 60 minutes in an hour. So that's going to be the same volume leaving the basin each hour. Then we can calculate the cumulative volume that's received in the basin. So from midnight to 1 a.m., we've got 990 cubic meters. But by 2 a.m., we've got those 990 cubic meters plus 792, which gives us a value of 1782. And we can just copy that equation down to fill in the rest of the cells. Now we can do a plot that shows the cumulative volume received during each hour. And since we have hour blocks of 1 hour each, so midnight to 1, 1 to 2, 2 to 3, to do the plot, we can show just kind of the halfway point between each of those time periods. So We'll use the 24-hour scale, meaning that from midnight to 1 a.m., we'll just put 0.5. From 1 to 2 a.m., we'll do 1.5, etc. All right, and then we can select the average flow rate coming into and leaving the basin, as well as those hours of the day, and plot them as you can see here. We can label those lines to be flow rate coming in and flow rate leaving, or flow rate out. So you can see the fluctuating flow rate coming in, and you can see the constant flow rate leaving the basin. All right, so next thing we can plot is the hours in the day with respect to the volume received. All right, so I'm just copying the template of this first graph, and then I'm just going to modify the data and the title. Volume received in the day. And I could just click on the data and drag it over to the appropriate column. So here we can see the cumulative volume received throughout the day. And we don't need this second line, so I'll just delete that. This is the plot that was shown previously in the worked out solution from the book. All right, now if we take a vertical line and we draw it from the point where the flow rate crosses, the flow rate in crosses the flow rate out, that is going to be the time of day when we have 0 cubic meters in the tank. In other words, it's going to be the time of the day when the tank is completely empty. And the reason is during the early hours of the morning, we're not really receiving that much flow, but we're pumping it out still at the same constant rate of 0.307 cubic meters per second. So if we now draw a parallel line to the line that connects point 0 and 0.24 hours, as you see here, we can estimate what the volume of the tank needs to be in order to accommodate this flow. And so it would be that vertical distance right there. However, we can also visualize that in a different way. And we can calculate it directly in Excel. So I'm just going to move this over, and we're going to add a few more columns to calculate here. Now you can see that this line, the place where the flow in and the flow out, those flow rates cross, that line falls somewhere between 8 and 9 a.m. All right, so it means sometime between 8 and 9 a.m. the tank is going to be completely empty. So now we can create a column here that's labeled the liquid volume in the basin at the end of each time period. So this is how much volume the basin actually has. And we, instead of starting at midnight like we did before with the volume received, we want to start at the time block between 8 and 9 a.m. So between 8 and 9 a.m. the tank is going to start filling up. And we can calculate that previous volume plus the volume that's received between 8 and 9 a.m. minus the volume that's discharged between 8 and 9 a.m. and we get 172 cubic meters. We can just take that equation now and copy it all the way down to the bottom. And we can even copy it back up to the top. However, we're going to have to shift the cell that's being referred to for that one cell so that it goes down and refers to the 11 to midnight hour. And we just copy all the way down, and we can fill in this entire column, which shows how the liquid volume in the basin changes throughout the day. All right, so now let's plot that. All right, so here you can see how the volume in the tank is changing throughout the day and how it reaches a volume of 0 between 8 and 9 a.m., and then it starts filling back up again, reaching its maximum volume somewhere around midnight. All right. So next, what we want to do is calculate the maximum value of what that volume is throughout the time period. And we can see that it's equal to 4,098 cubic meters. All right, so that would be the size that we need for this tank. All right, and you could see in the worked out solutions in the equations previously using the graphical method, the volume there was estimated slightly differently, and you got a slightly different value. In all cases, you would want to bump this value up by a factor of safety just to make sure that that your tank is large enough in order to equalize the flow. So next, what we want to do is calculate the concentration of BOD in the basin at the end of each time period so that we could see what effect this equalization basin has on the BOD loadings into the basin, into the treatment plant. All right, so again, we're going to start at that time period where there is no water left in the tank, and we're going to take the average BOD concentration during that time period, and we're going to multiply that by the volume received during that time period. To that, we're going to add what the BOD that was previously in the basin. And this value right now is blank, but later on we'll fill that in. And we're going to divide that by the cumulative volume, which is equal to the volume received during this time period plus the volume that was present in the basin at the end of the previous time period. All right, so that gives us a number, BOD concentration milligrams per liter. We're going to copy that down, and you can see the same equation here. It's now referring to cells one row below the previous time. Now in this one right here, we're just going to make sure that it is equal to 175, which is the concentration that's coming in during that period, because that's when the tank empties out completely. So whatever comes in, that's what concentration of BOD it's going to have. Now we can take the equation though and copy it down to the other cells. All right, so take this equation, copy and paste it down, and we can also paste it up into the first cell, and again revise which ones it's referring to make sure it's referring back to the 11 to midnight time frame for that calculation. And then we'll want to grab the equation from one of the other cells and paste it here and then copy it all the way down. Now you can see the BOD concentrations in the basin at the end of each time period. And this is assuming that the basin gets completely mixed. So whatever BOD was in there in the time period before is getting completely mixed with whatever BOD comes in the new wastewater. Last step is to calculate the BOD loadings coming into the basin and the BOD loadings that are leaving the basin. So instead of just the concentration, we want to look at the loading in terms of kilograms per hour. All right, so that's just equal to the concentration coming in multiplied by the flow rate. And then we just need to correct for the units. So the flow rate's got units of seconds. The concentration has units of liters and milligrams. So we can, milligrams per liter is the same as grams per cubic meter. So the cubic meters cancel out. We just need to multiply by 3,600 to correct seconds to hours, and then divide by 1,000 to correct from grams to kilograms. Same equation goes into the loading out. However, we're just going to refer to the BOD concentrations we calculated in the basin at the end of each time period, and of course the average flow rate that's leaving the basin, which is constant. All right, so now we have the BOD loadings coming into the basin. We've got the BOD loadings leaving the basin. We can plot these just like we plotted the flow rates coming in and leaving the basin. So using the same template, it's going to change the title. And now change the cell reference. Instead of the flow rates, just move that over to the loadings. Same thing with the effluent. Move that over to the loadings out. And we'd want to update the label here in our legend. BOD in, BOD out, for example. Now, if I were going to use one of these plots in a report, I would want to label it much more detailed. Like I would want to put x-axis labels, y-axis labels, units, make sure everything has units, and make it look as nice as possible. All right, and let's make this plot here, which shows the concentrations in and out, and show how that changes, or how that's different than the loadings in and out. All right, so the concentrations in clearly fluctuate, but again, the flow rates are also fluctuating. So the loading of BOD, which is basically the rate at which food is going to be delivered to the microorganisms in the treatment plant, that's going to be different because we have not only a changing BOD concentration, we've got a changing flow rate. So here you can see how the BOD loadings change throughout the day. You can see how the BOD loadings out have a lower peaks and lower valleys compared to the loadings in, which were fluctuating very drastically. So we can replicate the table that was shown in the previous solution from the book by calculating the maximum BOD loading in, dividing it by the average BOD loading in, and also looking at the ratio between the minimum BOD loading in and the average BOD loading in. And then we can look at the ratio between the peak and the minimum. Right, and by just copying that over, we can see that the ratios here have drastically improved. So the peak to average ratio is much lower than it was before. The minimum to average ratio is much closer to 1 than it was before. And the peak to minimum ratio is much, much lower. All right, let's shift gears a little bit and talk about screening. So the principal role of screening is to remove coarse materials from the flow stream that they might damage subsequent process equipments, pumps, etc. It's usually performed using coarse screens, which have larger gaps between them, followed by fine screens, which have smaller gaps between the screens. Coarse screens would be from 1/4 inch to 6 inches, and this would help protect pumps, valves, pipelines, and other elements in the system from being damaged or clogged. It can be hand cleaned or it can be mechanically cleaned. So the above photo shows a mechanically cleaned system. This bottom photo here would be a system that the operator has to come by and remove the materials with a rake. Then we have fine screens, which are up to 1/4 inch, and even micro screens, which are even smaller, which is not very commonly used. There's different designs for screens. So we've got static wedge wire screens, which have a shape kind of like this. So the feed water comes in through here. You've got the water kind of cascading down this curved section. It drains out through this port, and the solids get retained on the screen. All right, so solids get discharged down here. They're probably usually placed into a hopper to be removed off the site. And the screened wastewater goes down to the next treatment process. A drum screen looks like this. You've got a rotating cylinder, which is going to have the screen on the outside, as you can see here in the photo. The wastewater is coming in through a channel. It's going to pass through a screen. A screw pump is going to lift up those solids that are collected on the screen out into a hopper, and the screened sewage is going to pass through and go on to the next treatment process. Step screen is another design. This pretty much uses a mechanical action to lift up the solids, allowing the water to pass through, and that's how it mechanically kind of keeps the screen free of solids, and those are dumped off into a hopper. A vortex screen is another design. So you've got the drain. This is also used in stormwater, and the sewage comes in through an inlet and creates a vortex motion that causes the screenings to drop down to the bottom, and the water will exit through a different chamber into the effluent. So this can be installed as a structure within a pipe system. Again, that's why it's very commonly used in stormwater drains. Design considerations for screens are that in a wastewater treatment system, they need to be located before the grit chamber. We should design them with an appropriate approach velocity, which you can see some typical values that are used here for manual cleaning or for mechanical cleaning. You need to have clear openings between the bars. So if the bars start to get clogged, then you're going to have the failure of these systems. The system also produces a head loss through the screen. So there's some energy lost as the water moves through the screen. That can be calculated using the equation shown here. And then also we need to determine how the screenings are going to be handled. So typically they're hauled to a landfill. In some cases, they might be buried at the site itself, or even incinerated by themselves or in combination with sludge, grit, and or other materials. This would be common in larger installations. This table below shows some guidelines for typical values of the volume of screenings that you might find for different types of screens. So let's do an example problem. Determine the buildup of head loss through a bar screen when 50% of the flow area is blocked due to the accumulation of coarse solids. So let's assume the following conditions: that we have an approach velocity of 0.6 meters per second. The velocity through the clean bar screen is 0.9 meters per second. The open area for flow through the clean bar screen would be 0.19 square meters. And we can use a head loss coefficient of 0.7 for the clean bar. All right, so this is the equation we have to calculate the head loss through a coarse screen based on whether or not it's clean or clogged. So here we've got the coefficient C, which is equal to 0.7 when the screen is clean, and equal to 0.6 when the screen becomes clogged. We've also got VB, the velocity of the water going through the screen, and we've got VA, which is the approach velocity, the water coming up to the screen. So in this example, we are asked to determine the buildup of head loss through a bar screen when 50% of the flow area is blocked due to the accumulation of solids. And we've got some information about the approach velocity, the velocity through the clean bar screen, the open area of the screen, and the head loss coefficient that we're supposed to use for this particular screen, which again is 0.7. So the first step here is to calculate the head loss through a clean screen. So head loss is equal to 1 over 0.7 times 0.9 meters per second squared minus 0.6 meters per second squared. That whole thing divided by 2g, where g is equal to 9.81 meters per second squared. So this calculation gives us 0.033 meters. The next part of this example is to estimate the head loss through the clogged bar screen. So under this situation, the velocity going through the bar screen is going to increase because the area for the water to flow through has been reduced. and we're told that it's been reduced by 50%. So that means that it's going to double the velocity, right? So if you've got an opening through a screen with an area A and a flow rate, the velocity going through that opening is going to be equal to the flow rate divided by the area. If your area is reduced by half, and you've got the same flow rate going through that smaller area, then of course your velocity going through that area is going to double. All right, so that's the situation here. So instead of an approach velocity of 0.9, or sorry, instead of a velocity through the screen of 0.9, now our velocity v sub b is going to be equal to 0.9 times 2, or 1.8 meters per second. So now the head loss equation again, HL is equal to, in this case, 1 divided by 0.6, because we've got a clogged screen now, and then that's being multiplied by 1.8 meters per second minus 0.6 meters per second, which is still the approach velocity, and divide the whole thing by 2 times 9.81. That's going to give us a value of 0.24 meters. So you can see that this screen becomes 50% clogged. The head loss increases from 0.033 meters to 0.24 meters. All right, let's talk about settling and scouring. So in a grit chamber, the primary objective is to remove larger and heavier particles from the sewage before it gets treated biologically. Settling and scouring velocities are both important for the design of these processes, not just for grit chambers, but also for primary clarifiers. All right, so we have a dimensionless constant, beta, which ranges from 0.04 to 0.06. And we have a friction factor, which is taken to be in the range of 0.02 to 0.03. And you see the two different equations that we use here for, again, settling velocity and scouring velocity. So settling is all right, so the primary objective of grit chambers and also primary sedimentation tanks is to remove larger, heavier, settleable particles from the sewage before it gets treated biologically. So when we design these processes, the settling velocity and the scouring velocity are two important factors to consider. So settling velocity is the velocity at which the particles settle, and the scouring velocity is the velocity that will re-suspend those particles back up into the water column. All right, and they're both dependent on the density of the particles that are being settled or scoured and the density of the water, as well as some other factors like the diameter of the particle, the drag coefficient, and some dimensionless constants like beta, which ranges from 0.04 to 0.06 for sewage, and the Darcy-Weisbach friction factor, which ranges from 0.02 to 0.03. All right, so grit characteristics and quantities. In typical domestic sewage treatment plants, we get a combination of sand, gravel, other heavier materials that make their way into the sewage with characteristics that vary, but typically range from 13 to 65% moisture, very low to almost 0.5% volatile, and specific gravities which might range from 1.3 to up to 2.7. The quantities are also variable from system to system, but we have, up to from 0.5 to up to 5 cubic feet per million gallon for separate systems, and up to 24 cubic feet per million gallon for combined sewer systems. These grits, the grit that's collected here is typically sent to the landfill or, as I mentioned before, incinerated on site. All right, so grit chambers are used again for the removal of grit. The three types of grit chambers used in practice are the horizontal flow grit chamber, which is not really preferred anymore in newer systems, but historically has been used for grit chambers. It's a rectangular system, or in some case, a square system. Um, Less efficient than some of the newer designs like aerated grit chamber and vortex flow grit chamber. You can see here that we have differences in the specific gravity with respect to the equivalent size of the grit. So there have been studies done about, the characteristics of the grit that comes in to wastewater treatment systems, and in general, it's been found that the larger the grit size is, the higher the specific gravity is, until you get to kind of a low point, which might range from about 100 microns to about 250 microns, where you have very low specific gravity. And then anything below that would tend to be a higher specific gravity. This other plot down here shows the cumulative percent of grit that would pass through a screen of different sizes. So like if you have a sand equivalent size of, let's say, 150 microns, in some systems you might get, like 35% passing, 35% of the grit that passes through a screen with that size, 150 microns. In other systems, you might get more like 75%. So if it passes through a screen with that particular size, that means that the grit particles are either equal to or smaller than that size. Anything larger than that size would be retained. All right, so in general here, you've got a large variation, but you also have very few grit particles that are less than 50 microns. They're generally bigger than 100, 150 microns. All right, the design of horizontal flow grit chambers. There's three conditions that must be met. The first one is that the overflow rate of the chamber must be equal to the settling velocity of the grit particle. The second is that the horizontal velocity must be less than the scouring velocity of the inert particle. And the third is that the horizontal velocity must be greater than the scour velocity of organic particles. So traditional design philosophy specifies that grit chambers should be designed to capture 200 micron sand particles with specific gravity of 2.65. But as you can see from these plots shown in the previous slide, not all sand particles or grit particles have the same specific gravity. Some of them have much lower specific gravity, meaning that this traditional design philosophy that you might see in some design guidelines or standards, it's really just kind of a rule of thumb, and it's not exactly relevant for the true characteristics of grit. All right, but we do have some typical detention times that are used in design, like in the range of 45 to 90 seconds. Typical would be like 1 minute detention. Horizontal velocities that are typical to use in design, like 1 feet per second. Settling velocities for the removal of different size materials. So our settling velocity might be, from 2 to 4 feet per minute. And we can do an example problem just to demonstrate how this all comes together. So using these equations here for settling velocity and for scouring velocity, and using our knowledge of the equivalent size of grit and its specific gravity, let's do this example of what settling and scouring velocity will correspond with a 200 micron sand particle with a specific gravity of 2.65. All right, so let's assume that our 200 micron sand particle has this specific gravity. Of course, we know that in general, 200 micron particles in real systems tend to have slightly lower specific gravity. But let's start by assuming 2.65. So as a hint here, the dimensionless constant beta, which we can see in the scouring velocity equation, ranges from 0.04 to 0.06. The friction factor is 0.02 to 0.03. All right, so now that we've calculated that, consider the graphs shown here on the bottom right. The use of this 200 micron sand particle with Specific gravity 2.65, like I mentioned before, is based on tradition, and it's somewhat arbitrary. So looking at these plots, does it seem reasonable to use this as a guideline for design? Why or why not? All right, so let's start with the settling velocity in this example. So this is actually a review of a concept that we saw back in example 2-7 under the water treatment module. We are going to calculate the settling velocity using the iterative approach, starting with Stokes' law to calculate an initial velocity, and then we're going to check the Reynolds number and see if it's above or less than 1. And if it's above 1, we're going to then calculate the drag coefficient and use that in Newton's law, Newton's equation, to calculate the settling velocity, check the Reynolds number, recalculate the drag coefficient, etc., and repeat that process until we get a stable value for the settling velocity. So if we start with Stokes' law, now first we're going to have to make a few assumptions. For the purpose of this example calculation, we can just assume water with the following characteristics. So at about 20 degrees Celsius, water has a dynamic viscosity of 0.001 kilograms per meter per second and a kinematic viscosity of 10 to the negative 6th meters squared per second. And the density, we can assume it to be equal to 1,000 kilograms per cubic meter for this example. All right, so first, using Stokes' law, we calculate the settling velocity to be equal to 9.81 meters per second squared times 2650, based on the density that we're assuming in this example problem for a sand particle, minus 1,000. The units there are kilograms per cubic meter. Then we'll multiply that by our particle size, 200 microns, which is equal to 0.0002 meters, and that value gets squared. Divide that whole thing by 18 times the dynamic viscosity, which is equal to, we're assuming again, 0.001 kilogram per meter per second. All right, so the units all check out, and this gives us a value of 0.036 meters per second. All right, so then we're going to calculate the Reynolds number. That's equal to the particle diameter, 0.0002, times the kinematic viscosity, 0.000001 meters squared per second. And that's divided by, this is supposed to be the settling velocity, which is what we calculated up here, 0.036 meters per second, divided by the kinematic viscosity, which is 10 to the negative 6th meters squared per second. All right, so all the units cancel out, and this gives us a value of 7.19. All right, so that's clearly greater than 1. Therefore, we're going to calculate the drag coefficient, C sub D, and that is equal to 24 divided by the Reynolds number, plus 3 divided by square root of the Reynolds number, plus 0.34, gives us a value of 4.8. Now we're going to use that drag coefficient in Newton's law to calculate the settling velocity. So this is the first iteration, this will be the second iteration. All right, so according to Newton's law, we take the square root of 4 times 9.81 times 2650 minus 1000 times the particle size 0.0002. That whole thing is divided by 3 times the drag coefficient 4.8 times the density of water 1000. That is going to give us a value of 0.030 meters per second. All right, so you can see it's a little bit less than what we calculated the first time around. If we repeat this process, all right, so if we take this velocity here and we use it to calculate the Reynolds number, instead of 7.19, it's going to give us a value of about 6. Then we're going to use that to calculate the drag coefficient. That's going to give us a value of approximately 5.56. All right, and then we're going to use that in Newton's law to recalculate the velocity. And this next time around, we're going to get a value of 0.028. All right, so we repeat that process until this value stabilizes. And if we do that for about 7 or 8 iterations, we'll find that it stabilizes at a velocity equal to approximately 0.026 meters per second. All right, so that's the settling velocity. Next step is we're going to calculate the scouring velocity. So the equation for scouring velocity is equal to the square root of 8 times beta times the difference between the densities multiplied by g times the diameter divided by 1000 times the friction factor F. All right, so using our sand particle again, we've got 8 times beta. Now beta is a dimensionless constant and it's taken usually within the range of 0.04 to 0.06. 0.04 would be used in the case where we have material that's more similar to sand. 0.06 would be used in the case where we have material more similar to sticky matter like sludge. So in this case, we're going to use a value of 0.04 for beta, since we're dealing with a sand particle. When we get into clarification for secondary sludge, where instead of settling out heavier particles, we're settling out activated sludge flux, in that case, we're going to use a higher value for the dimensionless constant beta. All right, so here we've got 2650 minus 1000. Then we're multiplying that by the gravitational constant 9.81 times 0.0002. That whole thing gets divided by 1000 multiplied by F, which is usually within the range of 0.02 to 0.03. For this example, we'll just take half of that range, 0.025. All right, and that will give us a value of 0.203. meters per second. All right, so you can see for this sand particle, settling velocity is approximately 0.026 meters per second. So that's the velocity at which this particle is going to settle down to the bottom. The scouring velocity, which is the velocity of the flow that would resuspend the particle, is equal to 0.203 meters per second. So the example question asks, given the fact that this 200 micron sand particle with a specific gravity of 2.65 is really based just on tradition, it's somewhat arbitrary. If you look at some of the data that have been collected on the plots to the lower right, you can see that there are some deviations from that specific gravity based on the size of the grit particle. So the question is, does it seem reasonable to use this sand particle as a guideline for design, or should there be some other assumptions made? And the answer, I would say, given the fact that the majority of grit particles in most wastewater systems, based on the plots you see here, the majority of them have a size that's a little bit less than 200 microns. And in addition, for those particles that are 100 to 200 microns, the majority of those particles tend to have specific gravities that are much lower than 2.65. They're more along the lines of 1.52. So given that information, we can expect that the settling velocity of most grit particles would actually be slower than the settling velocity for the more dense sand particle of 200 microns. In addition to that, the scouring velocity for most grit particles in real systems would be lower than what we calculated here for a 200 micron sand particle. So I think it's time really that this use of a 200 micron sand particle with a specific gravity of 2.65, that concept should be discarded, and we should use better engineering judgment. If you are designing a system for grit removal, you should use engineering judgment based on what the actual characteristics are of the grit particle. All right, next let's look at the design guidelines for aerated grit chambers. So again, in aerated grit chambers, you've got wastewater coming in through an inlet, and it's coming through the chamber in a spiral flow pattern based on the geometry of the chamber. This drives those heavier particles down to the bottom, where you have a grit collection channel that collects all that grit, and the outlet, the liquid effluent, goes out of the system through a weir. All right, so the heavier grit settles while the lighter organics remain in suspension. The rate of air diffusion and the shape of the tank are what govern the rate of velocity and the flow of the water and how it rolls particles down to the bottom of the tank. All right, so we have some typical detention times at peak flow rate conditions. We've got some typical dimensions of the depth, length, and width. We've got ratios that should be adhered to: width to depth ratio, length to width ratio, and the amount of air that's supplied per unit of length. So the aeration helps keep the scum and some of the more organic, lighter organic particles helps keep those in suspension, because in this chamber we want to remove the grit, but we don't really want to settle out the organic material yet. That's what the primary clarifier is for. All right, and then we could also see, how much grit these systems tend to produce. A vortex grit chamber also has, these typical design ranges. So we've got wastewater brought into the chamber tangentially, and it again creates this vortex motion. So the inlet's here, the wastewater comes in, if you can see on a plan view, moves around in a spiral form, and then finally goes out through the outlet. The heavier grit, as it goes through the spiral, is driven downwards and is removed from the bottom here. All right, so the effluent outlet has twice the width of the influent flume. That produces a lower velocity exiting the system, which prevents the grit from being drawn back up into the affluent flow. All right, so we've got ranges for detention time, we've got ranges for diameter of the upper chamber, the lower chamber, we've got some height considerations and typical removal rates of grit of different sizes. Now there's trade-offs between these two different types of grit chamber designs. So you can see the advantages and disadvantages of aerated grit chambers. The advantages are that we've got efficiency that is constant over a wide range of flow rates, minimal head loss. The air rate can be tweaked to control the organic content that's removed. The chamber can also be used as a mixing chamber if we want to add some chemicals, for the subsequent process, which is primary sedimentation. If we want to add like a flocculant or some type of coagulant, right, to do coagulation, flocculation, enhanced primary treatment, we can use this chamber as mixing. Because we're aerating the wastewater a little bit, it might reduce the foul smells that would be produced due to septic conditions. However, the disadvantages are that it's got higher power consumption because we need to drive a pump the whole time to pump air into the system. We've got labor required because the air system creates fouling, has some maintenance issues that need to be taken care of from time to time. We may be releasing some volatile organic compounds because of the aeration. We might cause some odor issues. And there's labor associated with the maintenance, right? For the vortex grit chamber, it's also efficient over a wide range of flows. It's much more efficient than the aerated grit chamber in terms of energy consumption. The head loss is minimal. It has a smaller footprint, and there's really no moving pieces that are submerged. So because of that, it's easier to maintain, creates less maintenance issues, might be lower cost associated with labor for maintenance. The disadvantages are that the design is proprietary, meaning that you typically have to buy it from the manufacturers or deal with the proprietary nature of the design, meaning like that the design has a patent on it. All right, that's a disadvantage. The compaction of the grit is another disadvantage. The grit comes out quite more compact than in some other systems. Also, the blades used in the turbine could get clogged if there's rags or other kind of materials that get through the screening. So you want to make sure you have really good screening before you install a vortex grit chamber. So you don't want any of these materials to get into the vortex grit chamber, which could cause the malfunction. All right, and again, after grit removal, we send the wastewater off after the headworks and all that. We send it off to primary sedimentation. So primary sedimentation or clarification, its purpose is to remove the readily settleable solids and floating materials. This also reduces the suspended solids content of the sewage prior to biological treatment. Typically, primary clarifiers will remove 50 to 70% of suspended solids and 25 to 40% of BOD. All right, and we can predict the BOD and TSS removal using the following equation, where we've got some empirical coefficients here for A and B that you would see for BOD removal and TSS removal at a temperature of 20 degrees. The efficiency of the system may be different at different temperatures, but you can see here how the percent removal is also correlated with the detention time. So the amount of time that the wastewater stays in the system, on average, of course, is related to how much of the solids are removed. There is a kind of a point where the removal efficiency kind of flattens out. So you really don't want detention times that are very much higher than 4, 5, 6 hours. We can, as I mentioned before, we can add coagulants to aid and enhance the removal of TSS. We can use coagulants like ferric chloride or alum, just like we use in water treatment processes. So like 5 to 15 milligrams per liter of ferric chloride, or 0.1 to 0.15 milligrams per liter of polymer if we apply those coagulants and aids, it can increase the TSS removal to as high as 90%, right? So the treatment system that serves the majority of San Diego, the Point Loma treatment system, actually utilizes enhanced primary treatment with coagulation flocculation. All right, and this is what a primary clarifier looks like. So you've got clarifiers that have a circular design, just like with water treatment. You can have either a circular design or a rectangular design, and the concept is the same, but the geometry is different, right? So you've got, in the circular design, you've got the wastewater coming in through the influent, and it exits out from the center, moving towards the edge of the circle where you have effluent weirs. So the heavier solids will go down to the bottom and they'll slide down into a thickened sludge, which is removed from the system. The lighter materials in the water will flow up to the effluent weirs, which are located on the outside. So if we want to calculate the length of the weir for this clarifier, it's equal to the diameter, or sorry, not the diameter, the circumference of the primary clarifier. All right, we can also have a design where the influent is not in the center, but it's, you know, in the side. It's coming in through the side of the clarifier. And this is for, sorry, we can also have a rectangular design where the influent is coming in on one side rather than in the center of the clarifier, and it's moving horizontally across the clarifier. So in that case, the baffles are located at the end, and not baffles, sorry. In that case, the effluent weirs are located at the end of the clarifier, and the weir length is based on the length of the effluent troughs and how many there are. So you can calculate the detention time based on the volume of the clarifier and the flow rate. You can calculate the weir loading rate based on the length of the weirs and the flow rate. And we'll see some of the other differences associated with these two different designs for clarifiers in a minute. All right, so again, design considerations for clarifiers, and this is very similar to what we saw with water treatment. We've got the detention time, which is equal to the volume divided by the flow rate, just like in our previous examples, right? And we should correct the detention time for the temperature. So typically we would want to have about 2 hours of detention, but if we're operating at a colder temperature, we might choose a different detention time. So let's say that our temperature is 4 degrees or 6 degrees Celsius. We would look at this graph here and use a multiplier that's approximately equal to 1.5. So instead of 2 hours, maybe we want to use 2 times 1.5, which is 3 hours, right? Because it's a little bit less efficient at colder temperatures. If we're operating at 20 degrees, we can use the recommended detention time. All right, the second parameter that we consider for design is the surface loading rate, also known as the overflow rate. And again, if you remember from our water treatment sedimentation basin, this is equal to the flow rate divided by the surface area. All right, so typical overflow rates for primary sedimentation tanks, under average flow conditions, we want to be around 1,000 gallons per square foot per day, or 40 cubic meters per square meter per day. Under peak hourly flow conditions, we want it to be no higher than 2,500 or 3,000 gallons per square foot per day, or 100, 120 cubic meters per square meter per day. The weir loading rate should be approximately 20,000 gallons per foot per day, or 250 cubic meters per meter per day. All right, and then if we have primary settling with waste activated sludge return, so again, remember that in the waste activated sludge system, some of that sludge from secondary treatment comes back to the beginning of the system. In some cases, it might come after the primary clarifier, but in other cases, it might go back to the beginning of the headworks, in which case we would use slightly different values for the overflow rate in the primary settler. All right, another thing that we need to consider when designing primary cellars, primary sedimentation basins, is that ideally we want the flow to be uniform throughout the clarifier. So we want the flow to come in on the one side and flow uniformly through the system until it gets to the outlet. But in reality, we might have some short circuiting. So we might have thermal stratification. This happens when the water in the tank is warmer than the sewage coming into the system. In that case, the warmer water will rise to the top. You'll have this dead space here, and the sewage coming into the system will sink down to the bottom and take a short circuit, kind of a shortcut right to the effluent. So that's going to effectively make the volume of the tank a little bit smaller, and it's going to make the retention time a little bit shorter. We can also have thermal stratification when the water, sorry, this is a typo. This is when the water in the tank is colder. So the warmer water is going to rise to the top. And if you have warmer sewage coming into a cold tank, the colder water will be down at the bottom in a dead space. And the warmer water is going to rise to the top and exit through the effluent, creating, again, a short circuit that's effectively going to reduce your retention time. We could also have some wind conditions which produce this kind of wind-driven circulation cell that also creates this short circuit that, again, will effectively reduce our hydraulic retention time. So we want to take some of these factors into consideration. If we have a system where the temperature is highly fluctuating between night and day, then we might want to bump up our detention time by a little bit just to account for that short circuiting. All right, here's some typical dimensions for rectangular and circular sedimentation tanks. So, just for constructability and practicality, we don't want to use tanks that are too deep or too shallow. So like 14 feet is a typical depth. Diameters could range from 40 to 150 feet for circular basins, or the length of a rectangular basin might be between 80 and 130 feet. And then typical widths, so that you can see the width of a rectangular basin being quite a bit smaller than the length. We want to have these long and rectangular as opposed to square. The flow velocity or the flight speed, feet per minute, what some typical values and ranges are. So we want to make sure that our design falls in with these ranges. And again, like I mentioned before, we want to check our scouring velocity to make sure that we are not going to be resuspending the particles that we settle out. So we want to keep these horizontal velocities low. We can use the same equation as we used for the grit chamber to check the scouring velocity. However, we might use a slightly higher dimensionless constant. So 0.04 being more similar to sand, 0.06 being more similar to sticky matter like you might find in a primary clarifier with organic content. So we use a slightly higher dimensionless constant. We've got the Darcy-Weisbach friction factor, again, between 0.02, 0.03, and then specific gravity of sludge, which is going to be a lot lower than the specific gravity of grit. So we could take that in this example to be 1.05. All right, so here's the equation again for scouring velocity. Let's do an example problem. Suppose the average flow rate at a small municipal wastewater treatment plant is 20,000 cubic meters per day. If we have the highest observed peak daily flow rate is 50,000 cubic meters per day. Let's design a primary rectangular clarifier with a channel width of 6 meters. We're going to use a minimum of 2 clarifiers in parallel so that we have, flexibility to take one offline for maintenance if necessary. Let's estimate the BOD and TSS removal under average flow and peak flow conditions. And using an overflow rate of 40 cubic meters per square meter per day at average flow rate and a side water depth of 4 meters, let's determine the size of this reactor and check the scouring velocity to determine if the material will become resuspended or not. All right, so we've got a small wastewater treatment plant with 2 primary clarifiers in parallel. Each of them have a width of 6 meters, a side water depth of 4 meters, and we're going to use an overflow rate of 40 cubic meters per square meter per day. Now we're told that the average flow rate for this system is 20,000 cubic meters per day, and the peak flow rate is 50,000 cubic meters per day. So the first step to design these clarifiers is to calculate the required surface area. All right, and we do that, let's start with the average flow conditions. We do that using the overflow rate. So the area is equal to the flow rate divided by the overflow rate. So 20,000 divided by 40. And that gives us an area of 500 square meters. All right, so now, since we have a set width, we're going to be able to determine the length. So step 2, determine the dimensions. All right, so the area is 500. 500 divided by 6 is, and remember that we've got to multiply this by 2 because we've got two of these in parallel. That's going to give us a value of 41.7 meters for the length. All right, for convenience, we're just going to make this equal to approximately 42. Next step is to calculate the detention time. So first we need to figure out the tank volume. So step 3, we're going to check detention time. All right, so we've got the volume equal to 4 meters times 6 meters times 42. Now, 6 times 42, but we're also going to multiply this by 2 because remember we've got 2 tanks, and that is equal to 2016 cubic meters. All right, so the detention time then is the volume divided by the flow rate. So we've got 2016 cubic meters divided by 20,000 cubic meters per day. We can convert that to 24 hours per day. To get it in hours, that gives us a value of 2.4 hours. All right, next step is to check the detention time and the overflow rate under peak flow conditions. All right, so we've got a much higher flow rate during peak flow. And we want to check to make sure that the detention time and the overflow rate are still within acceptable range under those peak flow conditions. All right, so let's start with the overflow rate. Under peak flow conditions is equal to 50,000 divided by 2 reactors, and the dimensions are still 6 by 42. That's going to give us about 99 cubic meters per square meter per day. Detention time equal to volume divided by the flow rate. So under peak flow conditions, we've got 2016 divided by 50,000. Again, we'll convert it to 24 hours per day. It's going to give us a time of 0.97 hours. All right, and we would compare those then to our design guidelines to make sure they're within an acceptable range. Next step is we want to calculate the scouring velocity to see if it's within an appropriate level as well. That's not going to resuspend some of the particles that we've settled out. All right, so for scouring velocity equation, again, we've got V scour is equal to square root of 8 times beta times the difference in the densities. All right, multiplied by G and the particle diameter divided by 1000 times F. So let's use the following values for the cohesion constant. Let's use a value of 0.05. We're dealing now with primary sludge. It's a little bit more sticky than sand, but it's not quite as sticky as activated sludge. We've got the density. We can assume the density is equal to 1,250 kilograms per cubic meter. That's of the sludge. Got the density of the water. We can assume to be 1,000. Gravitational constant we know is 9.81. The particle diameter we can assume to be approximately 100 microns. All right, and the friction factor, again, we'll just take to be in the middle of the acceptable range, 0.025. So that's going to give us a scour velocity. If we plug in those values, we should calculate a scouring velocity of about 0.063 meters per second. Okay, so we're going to want to check that against our horizontal velocity to make sure that our horizontal velocity is not going to scour away those particles. So let's look at our horizontal velocity under the peak flow conditions, because that would be the time when it would be the highest. All right, so under peak flow conditions, we've got rectangular clarifiers here. And remember, the water depth is 4 meters. And this width is equal to 6 meters. So therefore, the surface area right here is 24 meters squared. So the horizontal velocity of flow under peak flow conditions is going to be equal to 50,000 cubic meters per day divided by this area, 24 meters squared. If we calculate that, it's going to give us 2,083 meters per day. All right, so divided by 24, divided by 60, divided by 60 gives us meters per second. So it's equal to 0.024 meters per second. And if we look at our scouring velocity, 0.063 meters per second, we are still below that scouring velocity. So even under peak flow conditions, we are not going to scour away a 100 micron particle of primary settled sludge. All right, so that checks out. Next, actually made a mistake here, is that we forgot to account for the fact that there are two of these. All right, so the scouring velocity would actually be even lower than this. Rather than 0.024, our area for one reactor is 24 square meters, but for two reactors, it's equal to 48 square meters. All right, so therefore, this value is going to be 0.012 meters per second. So still well below the scouring velocity for a 100 micron sludge particle. The last part of this problem is we want to estimate what the BOD and TSS removal is going to be for these clarifiers. All right, so under average flow conditions, we can estimate BOD removal using the equation based on the detention time. So equals detention time divided by A plus B times T. So that's equal to 2.4 divided by 0.018 plus 0.020 times 2.4 gives us a value of 36% for TSS removal. We've got the same equation but different coefficients for A and B. So here we've got 2.4 divided by 0.0075 plus 0.014 times 2.4, which gives us an estimate of 58%. All right, so that would be under average flow conditions. Under peak flow conditions, our retention time was reduced to about 0.99 hours. And so if we plug that in to this equation and this equation, we're going to get a BOD removal of 26% and a TSS removal of 46% approximately. All right, so it gives you a rough idea of what to expect in terms of the percent removal of those constituents.